Welcome to your complete Q&A guide for the WGU Anatomy and Physiology eye exam. We'll break down real exam questions. Why one answer wins, why others miss, and the theory behind each. First up, Domain 1. Chemistry, cells and body organization. Covering the body's hierarchy of organization and essential features of life. Homeostasis and the feedback mechanisms keeping the body stable. Anatomy vocabulary, directional terms, planes and body cavities. Essential chemistry, matter, atoms and bonding. Reactions, energy changes and chemical equilibrium. Inorganic compounds, water, acids, bases and pH. Don't forget, you can grab free exam guides and practice questions from our website to help you conquer your D312 exam. Just check the link right in the description below to get instant access. It's the smart way to prepare so you can study smarter, not harder, and pass with confidence. Alright, let's jump right in. Question 1. A nursing student is reviewing how the human body is built from its simplest components up to the whole person. The instructor asks the student to arrange the 6 levels of structural organization in order, beginning with the simplest. Which sequence is correct? Your options are A. Cellular, chemical, tissue, organ system, organ, organism. B. Chemical, tissue, cellular, organ system, organism. C. Chemical, cellular, tissue, organ system, organism. D. Cellular, tissue, chemical, organism, organ system. Which one is it? Pause the video if you need more time. The correct answer is C. Chemical, cellular, tissue, organ system, organism. C is correct because the hierarchy moves from atom and molecules at the chemical level to cells, to tissues made of similar cells, to organs made of 2 or more tissue types, to organ systems, and finally to the whole organism. Each level is constructed from the components of the level beneath it. A is wrong because this sequence places the cellular level before the chemical level, which reverses the actual relationship. Molecules must exist before they can be assembled into organelles and cells. B is wrong because this places tissue above the chemical level but below the cellular level. Tissues are groups of similar cells, so cells must come first. D is wrong because this sequence buries the chemical level in the middle and ends with organ system after organism. The organism is the most complex level and always comes last. A single misspelled letter in the hemoglobin gene can eventually harm an entire person because the body is built as a hierarchy, and damage at one level ripples through every level above it. The body is organized into 6 structural levels, each built from the one below it: chemical, cellular, tissue, organ system, and organism. The cellular level is the smallest unit that can properly be called alive. The stomach makes the tissue-to-organ boundary concrete. Epithelial tissue secretes acid, smooth muscle churns. Connective tissue binds and carries vessels. And nervous tissue coordinates timing. 4 tissue types, 1 coordinated function, 1 organ, case. Strip away 3 and what remains is tissue, not an organ. A common mix-up swaps 2 counts. There are 6 levels of organization, but 11 organ systems, including integumentary, skeletal, muscular, nervous, endocrine, cardiovascular, lymphatic, respiratory, digestive, urinary, and reproductive. All 11 are simply examples of the 5th level, with the organism as the level above them. Watch for exam language like built from, composed of, or an ordering from simplest to most complex. That signals the hierarchy is being tested. If the question instead asks why a structure has its particular shape, that's complementarity of structure and function, a related but separate idea. Question 2. A student examining a slide of small intestine notices that the lining cells are covered with thousands of tiny finger-like projections. The instructor explains that these projections dramatically increase the amount of surface available for absorbing nutrients, which foundational principle of anatomy and physiology does this observation illustrate. Your options are A. The complementarity of structure and function. B. The principle of dynamic equilibrium. C. The cell theory principle that all cells arise from pre-existing cells. D. The hierarchy of structural organization. Take a second. Which answer would you pick? The correct answer is A. The complementarity of structure and function. A is correct because complementarity of structure and function states that a structure's form is precisely suited to the job it performs. Microvilli exists because absorption depends on surface area, so the shape of the cell surface directly serves its function. B is wrong because dynamic equilibrium describes how homeostasis holds variables within a narrow range around a set point. It concerns regulation over time, not the fit between anatomical form and physiological job. C is wrong because the cell theory principle about cells arising from pre-existing cells addresses the origin of new cells through division. It says nothing about why a cell shape matches its role. D is wrong because the hierarchy of structural organization describes the 6 levels from chemical to organismal. It organizes the levels but does not explain why a given structure has the shape it has. Structure always determines function. This idea, called the complementarity of structure and function, says the shape of any body part is precisely suited to the job it performs, from single molecules all the way up to whole organs. Anatomy and physiology grew up as separate fields. Anatomy described shape through dissection, while physiology asked how things work. Studied alone, neither lets you predict anything, but complementarity bridges them, turning memorized shapes into working inferences. The mechanism is mostly geometry. A red blood cell is flattened to shorten the distance oxygen must travel. The intestinal lining folds into villi and microvilli to multiply absorptive surface, and the left ventricle's thick muscular wall generates the pressure needed to pump blood through the entire body, while the thinner right ventricle only pushes blood to the lungs. Used as a method rather than an observation, complementarity runs in both directions. A structure with enormous surface area suggests absorption or exchange. A structure built for strength suggests load-bearing. And a cell packed with energy-making organelles suggests sustained work. Whether a stem describes a structure and asks what it's for, or describes a function and asks for the matching structural adaptation, the answer always takes the same shape. Form serves job. Question 3. A patient recovering from major surgery is placed on a high-protein diet so the body can join amino acids together to rebuild damaged muscle tissue. These building reactions consume energy rather than release it. Which metabolic term describes this phase of metabolism? Your options are A. Catabolism, B. Excretion, C. Decomposition, D. Anabolism. Before I reveal it, which one do you think is right? The correct answer is D. Anabolism. D is correct because anabolism is the constructive phase of metabolism in which smaller molecules are joined into larger ones, and it requires an input of energy. Building muscle protein from amino acids is a textbook anabolic process. A is wrong because catabolism is the opposite phase, breaking larger molecules into smaller ones and releasing energy. Digesting protein into amino acids would be catabolic, but assembling them is not. B is wrong because excretion is the removal of metabolic and digestive wastes, such as carbon dioxide, urea, and feces. It is a separate necessary life function and does not describe protein construction. C is wrong because decomposition names a chemical reaction pattern in which a larger molecule is split into smaller pieces. That is the reverse of what is happening when amino acids are linked together. Metabolism is every chemical reaction in the body, and it splits along one line. Reactions either build or they break. Anabolism joins small molecules into large ones and stores energy in the new bonds, so it costs energy. Catabolism breaks large molecules apart and releases that stored energy. ATP is the intermediary. Catabolism charges it up. Anabolism spends it. The body doesn't run these phases separately. Fuel gets dismantled. The released energy attaches a phosphate to ADP to make ATP, and that ATP is spent wherever construction is needed. It's tempting to think catabolism is the damaging phase and anabolism the healthy one, but that's wrong. Catabolism is how a cell gets every unit of usable energy it has. Growth happens when anabolism outpaces catabolism. Wasting happens when catabolism outpaces anabolism. On layer down, anabolism is the category, synthesis is its pattern, and dehydration synthesis is the mechanism, catabolism decomposition, and hydrolysis mirror that on the other side. Answering at the wrong level of that ladder is the most common mistake. Question 4. An emergency response team follows the ABCs of resuscitation and works to restore airway and breathing before addressing any other need. A student asks why this need takes priority over food and fluids. Which explanation is most accurate? Your options are: A. Nutrients take priority because the body cannot store glucose for more than a few minutes. B. Oxygen takes priority because the body cannot store it, and the reactions that release energy from food are oxidative. C. Water takes priority because it makes up 50 to 60% of adult body weight. D. Appropriate atmospheric pressure takes priority because breathing depends entirely on it. What's your answer? Commit to one before I continue. The correct answer is B. Oxygen takes priority because the body cannot store it, and the reactions that release energy from food are oxidative. B is correct because no nutrient can be converted into usable cellular energy without oxygen, because the energy-releasing reactions are oxidative. Since the body has no oxygen reserve, brain cells begin dying within minutes of interruption. A is wrong because the body does store carbohydrate as glycogen in liver and muscle, and a person can survive weeks without food. Nutrients are essential but far less time critical than oxygen. C is wrong because water is indeed the most abundant substance in the body, but a person can survive several days without it. Abundance is not the same as urgency. D is wrong because atmospheric pressure matters because gas exchange depends on it, but it is a background environmental condition rather than the immediate target of resuscitation. Restoring airflow addresses oxygen delivery directly. Paramedics follow airway, breathing, circulation in that order for a reason. It's a ranking of survival needs by how fast their absence kills. You can survive weeks without food, days without water, but only minutes without oxygen. The necessary life functions depend on 5 survival needs. Nutrients supply energy and building material. Oxygen releases energy from those nutrients. Water is the fluid medium for chemical reactions. Normal temperature keeps reactions running at a workable rate. And appropriate atmospheric pressure allows gas exchange in the lungs. Oxygen is special for 2 precise reasons. First, releasing energy from nutrients is an oxidative process, so nothing becomes usable energy without oxygen. Second, unlike carbohydrates stored as glycogen or fat stored in adipose tissue, the body keeps no oxygen reserve at all that must arrive continuously. Inside the cell, oxygen combines with nutrients to release usable energy, a continuous chemical partnership with no stockpile to fall back on if the supply stops. Water makes up 50 to 60% of body weight, making it tempting to call the most critical need, but abundance and urgency are different measurements. When a question describes an emergency or resuscitation, it's almost always asking about oxygen, not water. Question 5. A researcher prepares stained slides of cardiac muscle and studies how the cells are arranged into interconnected sheets within the heart wall. The work focuses on the organization of groups of similar cells rather than on individual cell interiors or on organs visible to the naked eye. Which subdivision of anatomy does this research represent? Your options are A. Histology, B. Cytology, C. Gross anatomy, D. Embryology. Pick one, trust your gut. Here's your chance to test yourself. The correct answer is A. Histology. A is correct because histology is the microscopic study of tissues, meaning groups of similar cells working together. Examining how muscle cells are organized into sheets is exactly a tissue-level question. B is wrong because cytology is the microscopic study of individual cells and their internal structures. The described work looks past the single cell to how cells are arranged as a group. C is wrong because gross anatomy studies structures large enough to be seen without magnification, such as the heart as a whole organ. Slides in a microscope place this work in microscopic anatomy. D is wrong because embryology examines structural changes that occur before birth. Nothing in this scenario involves prenatal development. Anatomy studies structure, physiology studies function, but neither field can stay one piece. Both split further, and knowing why they split is the real exam skill. Gross anatomy covers what the naked eye can see, like the heart or the femur. Once you need a microscope, you're in microscopic anatomy, which splits into cytology, the study of cells, and histology, the study of tissues. Developmental anatomy tracks change over a lifetime, and embryology narrows that to before birth. Physiology doesn't divide by scale at all. It divides by organ system, giving us renal physiology, neurophysiology, and cardiovascular physiology. This asymmetry is the point. Structure is sorted by how big it is. Function is sorted by who performs it. A pathologist reading a biopsy does both in sequence. Low power checks tissue architecture and arrangement. That's histology. High power checks individual cell, nuclei, and organelles. That's cytology. Same slide, two genuinely different questions. Don't confuse this with the hierarchy of structural organization. That's about how the body is built. These terms are about how the body is studied. And the tell is whether the stem describes a person doing work or a structure nested inside another. Question 6. Blood pressure in a healthy adult rises briefly after a burst of physical exertion. Stretch-sensitive structures in the walls of the aorta and carotid arteries register the increased stretch and send signals toward the brain stem. Which component of a homeostatic feedback loop do these stretch-sensitive structures represent? Your options are A. Effector, B. Control center, C. Receptor, D. Set point. Which would you go with? Lock it in before the reveal. The correct answer is C. Receptor. C is correct because a receptor is the component that monitors the environment and detects a change in the regulated variable. Baroreceptors sense arterial stretch and send input along an afferent pathway toward the control center. A is wrong because an effector is the structure that carries out the response, typically a muscle or gland. In this loop, the heart and vascular smooth muscles serve that role, not the stretch sensors. B is wrong because the control center analyzes incoming information and decides on a response. That role belongs to the cardiovascular center in the medulla oblongata, which receives the baroreceptor signal. D is wrong because the set point is the target value the system defends, not a physical structure. It is a property determined by the control center rather than a component that detects change. Every homeostatic control system in the body, no matter which variable it defends, is built from exactly three components: Learning these three well matters more than memorizing individual examples, because they let you take apart any unfamiliar scenario on site. A receptor detects change in the regulated variable. A control center compares that signal to a set point and decides on a response. An effector, usually a muscle or gland, carries the response out and alters the variable. The baroreceptor reflex shows the loop clearly. Rising blood pressure stretches the aorta and carotid arteries. Baroreceptors fire along the afferent pathway to the brainstem. The cardiovascular center in the medulla compares the signal to its target, and efferent signals reach the heart and vessels to slow the heart and dilate the vessels, bringing pressure back down. A set point is not a component, it's just the target value the control center defends. And a single structure can occupy two roles at once. The hypothalamus senses temperature and also acts as the control center, while pancreatic beta cells detect rising glucose and secrete the insulin that answers it. Exam verbs give it away: detects, senses, and monitors point to a receptor, compares, integrates, and directs point to a control center, contracts, secretes, and dilates point to an effector. Locate the verb and you locate the component being tested. Question 7. After a meal, blood glucose climbs above its normal fasting range. Pancreatic beta cells release insulin. Body cells take up glucose and store it as glycogen, and blood glucose falls back toward the normal range. Which statement best characterizes this control mechanism? Your options are: A. Positive feedback because the response amplifies the original stimulus. B. Negative feedback because the response reverses the original stimulus. C. Positive feedback because two antagonistic hormones are involved. D. Negative feedback because the variable is driven further from its set point. Don't overthink it, which one feels right? The correct answer is B. Negative feedback because the response reverses the original stimulus. B is correct because in negative feedback, the effector response opposes the change that triggered it. Glucose uptake lowers the very variable that rose, returning it toward the set point and shutting the loop off. A is wrong because positive feedback would mean the response drove glucose even higher. Insulin does the opposite by removing glucose from the blood. C is wrong because the presence of antagonistic hormones such as insulin and glucagon does not make a loop positive. Both hormones work through negative feedback, simply pushing glucose in opposite directions. D is wrong because negative feedback returns a variable toward its set point rather than away from it. Movement further from the set point is the signature of positive feedback. Negative and negative feedback describes a direction, not a verdict. It means the response runs opposite to the stimulus that triggered it, not that something harmful is happening. Two consequences follow immediately. Negative feedback is stabilizing, keeping a variable oscillating gently around its target, and it's self-limiting, since the response cancels the very stimulus that produced it, so the loop shuts itself off without outside instruction. Blood glucose regulation shows the pattern in full. After a meal, beta cells sense rising glucose and release insulin, which drives cells to store glucose as glycogen. When glucose falls, alpha cells release glucagon, which drives the liver to release glucose back into the blood. Insulin and glucagon push the same variable in opposite directions, but each is running its own separate negative feedback loop. Thermoregulation and blood pressure control follow the identical logic. Rising temperature triggers sweating to cool down. Falling temperature triggers shivering to warm up. And rising blood pressure triggers a slowed heart and dilated vessels. Every response cancels the change that caused it. The test is never how many hormones are involved or how dramatic the response looks. Negative feedback returns a variable toward its set point and shuts itself off, while positive feedback drives it further away and cannot stop itself. Question 8. During labor, the descending head of the fetus stretches the cervix. Stretch signals trigger oxytocin release. Oxytocin drives stronger uterine contractions, and those contractions push the head harder against the cervix, producing still more stretch. Which choice correctly identifies this mechanism and pairs it with another example of the same type? Your options are A. Negative feedback, like the baroreceptor reflex correcting a rise in blood pressure. B. Negative feedback, like shivering in response to falling core temperature. C. Positive feedback, like sweating in response to rising core temperature. D. Positive feedback, like the platelet cascade during blood clotting. Got a guess? Lock it in. The correct answer is D. Positive feedback, like the platelet cascade during blood clotting. D is correct because the uterine response amplifies the original stretch stimulus, driving the process toward completion, which defines positive feedback. Blood clotting works the same way, as activated platelets release chemicals that recruit still more platelets. A is wrong because the baroreceptor reflex opposes a pressure change and returns pressure toward normal, making it negative feedback. It also mislabels the labor mechanism. B is wrong because shivering opposes falling temperature by generating heat, which is negative feedback. The labor cycle intensifies rather than opposes its stimulus. C is wrong because the mechanism type is correctly named here, but sweating is a negative feedback response that cools the body and cancels the stimulus. The pairing is wrong. The body regulates dozens of variables, but positive feedback runs almost none of them, and that scarcity is the key clue. Positive feedback amplifies whatever triggered it, pushing a variable further from baseline instead of back toward a target, so it has no internal brake and is used only when a process must be driven fast to completion. Labor is the classic example. The fetal head stretches the cervix. Stretch receptors signal the hypothalamus and posterior pituitary to release oxytocin. Oxytocin strengthens uterine contractions, and stronger contractions increase the stretch even more. Each turn intensifies the next, and the loop only breaks when the infant is delivered and the stretch disappears. Homeostasis works the same way. Platelets recruit more platelets, and clotting factors activate each other until a fibrin mesh seals the vessel. The neuron's action potential and the LH surge that triggers ovulation escalate identically, and in every case something outside the loop, not the loop itself, brings it to an end. The costliest mistake is assuming positive means good. It only describes direction. So the same amplifying mechanism that helps in labor and clotting is lethal in shock or a runaway fever. Watch for signal words like amplifies and cascade. And remember that dramatic escalation alone isn't proof, since sweating during exercise is a dramatic response that is still negative feedback. Whenever a cycle continues until an outside event stops it, that is the clearest sign of positive feedback. Question 9. A person exercising outdoors begins to overheat. The hypothalamus compares incoming temperature information against a reference value, judges the body too warm, and directs sweat glands and cutaneous blood vessels to respond. Which role does the hypothalamus play in this loop? Your options are A. Control center, because it holds the set point and determines the appropriate response. B. Receptor, because thermoreceptors are located within it. C. Effector, because it produces the sweating response. D. Afferent pathway, because temperature information travels through it. Which one is it? Pause the video if you need more time. The correct answer is A. Control center, because it holds the set point and determines the appropriate response. A is correct because the control center holds the set point, evaluates input from receptors, and issues output along the efferent pathway. The hypothalamus performs all three of these jobs during thermoregulation. B is wrong because the hypothalamus does contain thermoreceptors, but detection is not the role being described in this scenario. The described action is comparison against a set point and selection of a response, which is integration. C is wrong because the effectors here are the sweat glands and the smooth muscle of cutaneous blood vessels. The hypothalamus commands them, but does not itself carry out the cooling response. D is wrong because an afferent pathway is the route that carries input toward the control center, not the center itself. The hypothalamus is the destination of that pathway. When a runner overheats, thermoreceptors report the rise in temperature, but something has to decide what that report means. That decision-making job belongs to the control center, and it's the most misidentified component in any feedback loop. A control center does three things. It holds the set point, it analyzes incoming input against that set point, and it determines the appropriate response. Detection belongs to the receptor, execution belongs to the effector, but judgment belongs here. The hypothalamus itself contains thermoreceptors, so it can sense and decide at once. If the question emphasizes detecting a change, that's the receptor role. If it emphasizes comparing against a set point and choosing a response, that's the control center role. The hypothalamus sets points for temperature, water balance, and hormone axes. The medulla oblongata's cardiovascular center defends blood pressure, and pancreatic islet cells act as control centers for blood glucose, since one cell can detect and respond without help. The same structure can carry two labels if it performs two functions. Always ask what the structure is doing in the sentence. Sensing makes it a receptor. Deciding makes it a control center, and acting makes it an effector. Question 10. A trauma patient in circulatory shock has severely low blood pressure. The reduced pressure lowers blood flow to the heart muscle. The weakened heart pumps less effectively, and blood pressure drops further. Which statement best explains why the situation is so dangerous? Your options are A negative feedback loop has become oversensitive and is overcorrecting the pressure drop. B, the set point for blood pressure has been permanently reset by the medulla oblongata. C, a positive feedback cycle is amplifying the original change and cannot terminate itself without outside intervention. D, the baroreceptors have stopped detecting stretch, so no feedback of any kind is occurring. Take a second. Which answer would you pick? The correct answer is C. A positive feedback cycle is amplifying the original change and cannot terminate itself without outside intervention. C is correct because positive feedback loops are self-amplifying and are not self-limiting, so they intensify until some external event interrupts them. In shock, this produces a downward spiral that requires medical intervention to break. A is wrong because an oversensitive negative feedback loop would still push the variable back toward normal. The defining feature of this scenario is that each step worsens the original problem. B is wrong because a reset set point would change the target value the body defends, not create a self-escalating spiral. Nothing described suggests the medulla has adopted a new target. D is wrong because baroreceptors continue to fire, and their reduced signaling is part of what drives the compensatory response. The problem is amplification of the change, not an absence of detection. Circulatory shock kills through a mechanism that inverts everything reassuring about the body's control systems. Falling blood pressure reduces coronary perfusion, weakening the heart, which drops pressure even further. Each step worsens the one before it, and the spiral tightens until something from outside interrupts it. This general failure is called homeostatic imbalance, and most disease can be understood in these terms. A blood pH outside normal range, a fever that won't break, a glucose that stays high, each is a control system that has stopped controlling. Aging produces a gentler version as receptors lose sensitivity and feedback loops lose precision over time. The mechanism that makes this dangerous is a shift in which type of feedback is running. Ordinarily, protective negative feedback dominates, but once overwhelmed, destructive positive feedback takes over. A dangerously high fever works the same way. Heat accelerates metabolism, and metabolism generates more heat, feeding the loop with no internal break. Only one of 3 similar sounding explanations produces a true emergency. Oversensitive negative feedback still pushes the variable back toward normal. A reset set point, like fever's initial rise, defends a new target. Only runaway positive feedback drives the variable away with nothing to stop it, and only that one requires outside intervention. Exam language about spirals, vicious cycles, or deterioration that continues until treatment points to positive feedback. Drift means correction is missing. A spiral means correction has been replaced by amplification, and that difference is what makes it the emergency. Question 11. A physical therapist charts the location of a forearm fracture, noting that the break sits closer to the elbow than to the wrist. The therapist must describe the fracture site relative to the wrist using standard anatomical language. Which directional term is correct? Your options are A. Distal, B. Proximal, C. Superficial, D. Medial. Before I reveal it, which one do you think is right? The correct answer is B. Proximal. B is correct because proximal means closer to the point where a limb attaches to the trunk. A break near the elbow is closer to the shoulder attachment than the wrist is, so it is proximal to the wrist. A is wrong because distal means farther from the point of limb attachment. The wrist is distal to the fracture, not the other way around. C is wrong because superficial describes position relative to the body surface, meaning toward the outside. It says nothing about position along the length of a limb. D is wrong because medial means toward the midline of the body. Along a forearm, the relevant axis is attachment distance, not distance from the midline. Saying a fracture is up the arm means nothing in a chart, because up depends on the patient's position, and arm covers a lot of ground. Directional terms fix this by describing one structure relative to another along a defined axis, and each pair measures a different axis. That single organizing factor is what makes the whole system learnable. Superior and inferior run head to foot, so the heart is superior to the stomach. Anterior and posterior run front to back, so the sternum is anterior to the spine. Medial and lateral run toward or away from the midline, so the nose is medial to the eyes while the ears are lateral. Superficial and deep run from the surface inward, so skin is superficial to muscle and bone is deep to it. Proximal and distal work differently. They apply to limbs and measure distance from where the limb attaches to the trunk. The shoulder is proximal, the hand is distal, and the elbow sits proximal to the wrist but distal to the shoulder, because the reference point is the attachment, not the midline or the head. These terms can't be swapped for medial, lateral, or superior, inferior. The costliest mistake is mixing up axes. A structure can be deep and still anterior, since those measure different things. Exam stems reveal the intended pair by naming the reference structure. Wrist, elbow, or shoulder signals proximal or distal, while the midline, nose, or ear signal medial or lateral. Ipsilateral and contralateral are a different kind of term entirely, describing sidedness rather than distance along an axis. Question 12. A patient is placed face up on the examination table for an abdominal ultrasound, with both hands resting palms down at the sides. While charting, the nurse must name the patient's position and also describe where the thumb sits relative to the other fingers. Which statement is correct? Your options are A. The patient is prone and the thumb is medial to the other fingers because the palms are turned down. B. The patient is supine and the thumb is medial to the other fingers because the palms are turned down. C. The patient is prone and the thumb is lateral to the other fingers regardless of how the hand is turned. D. The patient is supine, and the thumb is lateral to the other fingers regardless of how the hand is turned. What's your answer? Commit to one before I continue. The correct answer is D. The patient is supine and the thumb is lateral to the other fingers regardless of how the hand is turned. D is correct because supine means lying face up on the back. All directional terms are defined as though the body were in the anatomical position with palms forward. So the thumb is always described as lateral no matter how the hand actually rests. A is wrong because prone means lying face down, which contradicts the described position. The medial claim also abandons the anatomical position convention. B is wrong because the position term is right, but the thumb description is wrong. Directional terms never change based on the body's actual orientation, which is the entire reason the anatomical position exists as a standard. C is wrong because the thumb description is correct, but prone describes a face-down patient. This patient is face up. Imagine a patient face down, one arm twisted behind the back, palm turned up. Describing the thumb's position now depends entirely on how the limb happens to be twisted, and no two clinicians would agree. Anatomy solves this by defining every directional term against one fixed reference posture, no matter what the body is actually doing. The reference posture is specific: standing erect, facing forward, feet flat and slightly apart, arms at the sides, and palms turned forward with thumbs pointing away from the body. That forward-facing palm is the detail most often forgotten, because a person's natural resting posture has palms facing the thighs instead. Supine means lying face up on the back. Prone means lying face down on the belly. Unlike directional terms, these describe an actual physical position, and clinicians use them constantly because patient positioning affects exams, imaging, and breathing. Because directional terms are locked to anatomical position, the thumb is always lateral to the fingers, whether the patient is standing, supine, prone, or twisted into any position. The terms describe fixed relationships, not momentary geometry, so a clinician never has to recalculate direction based on how a patient is lying. The tempting mistake is to see a palm turned downward and relabel the thumb as medial, but that defeats the entire purpose of the standard. This is exactly why radiology reports and operative notes stay reliable across any patient position, and why exam stems describing unusual postures are testing whether you'll abandon the convention. Question 13. A radiologist orders an imaging study that will produce a vertical slice separating the front of the body from the back, allowing the chest wall and the structures behind it to be compared in a single view. Which plane produces this section? Your options are A. Transverse plane, B. Mid-sagittal plane, C. Frontal plane, D. Oblique plane. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is C. Frontal plane. C is correct because the frontal plane, also called the coronal plane, is a vertical plane that divides the body into anterior and posterior portions. Picturing a plane passing through both ears from side to side makes the orientation clear. A is wrong because a transverse plane is horizontal and divides the body into superior and inferior portions. It produces the cross-sectional slices familiar from CT imaging. B is wrong because a mid-sagittal plane runs vertically down the midline and divides the body into equal right and left halves. It separates sides, not front from back. D is wrong because an oblique plane is any cut made at an angle to the three standard planes. It distorts proportions and is rarely used for clinical imaging. Every scan or dissection depends on a cut along a flat surface called a plane. Standardizing these planes gave medicine a shared visual language, so a scan from one city can be read anywhere. Three principal planes sit at right angles to one another. The sagittal plane divides right from left, the frontal or coronal plane divides front from back, and the transverse or horizontal plane divides top from bottom. An oblique plane is simply any angled cut across these three. The sagittal plane splits further. A mid-sagittal or median plane runs exactly down the midline for equal halves, while a parasagittal plane lies off-center and creates unequal portions. Remember, every mid-sagittal plane is sagittal, but most sagittal planes are not mid-sagittal. The most reliable trick is to ignore the blade and name what the cut separates. Right from left means sagittal, front from back means frontal, and top from bottom means transverse. The single reframing eliminates most errors. Don't confuse planes with directional terms like anterior or superior. Direction describes where one structure sits relative to another, while a plane describes how the body is divided, and oblique cuts, though sometimes necessary, distort proportions, which is why they're less useful for measurement. Question 14. A patient who sustained damage to the right side of the brain now shows weakness in the left arm and left leg. A student asks how to describe the anatomical relationship between the damaged brain region and the affected limbs. Which term applies? Your options are A. Contralateral, B. Ipsilateral, C. Intermediate, D. Distal. Which would you go with? Lock it in before the reveal. The correct answer is A. Contralateral. A is correct because contralateral means on the opposite side of the body. Damage on the right side of the brain producing weakness on the left side is the standard contralateral pattern seen in neurology. B is wrong because ipsilateral means on the same side. That would describe right brain damage causing right-sided weakness, which is not what is observed here. C is wrong because intermediate describes a structure position between a more medial and a more lateral structure. It is a side-to-side position term, not a same-side or opposite-side relationship. D is wrong because distal describes distance from the point where a limb attaches to the trunk. It compares positions along a limb rather than across the body's two halves. Why does damage to the right side of the brain cause weakness in the left arm and leg? Answering that requires two special terms that describe relationships between sides, not positions on the body. Ipsilateral means on the same side of the body, while contralateral means on opposite sides. Both are purely relational. The right arm and right leg are ipsilateral to each other, but the right arm and left leg are contralateral. These terms matter so much in neurology because major motor pathways cross from one side of the nervous system to the other as they travel between brain and body. That crossing is why a lesion in one hemisphere produces weakness on the opposite or contralateral side. Exams love to mix these up with true directional terms. Medial and lateral measure distance from the midline. Superior and inferior measure head to foot position. And proximal and distal measure distance from a limb's attachment, but ipsilateral and contralateral measure nothing. They only classify same side versus opposite side. Whenever a stem mentions stroke, hemisphere, or one-sided weakness, think sidedness first. Reaching for medial or lateral when the question is really about same side versus opposite side is the most common way to lose this point. Question 15. A clinician documents fluid accumulation and swelling in the hollow at the back of a patient's knee. Precise regional terminology is required for the chart because the anterior aspect of the knee is a different structure entirely. Which regional term names this location? Your options are A. Patella, B. sural, C. crural, D. popliteal. Don't overthink it, which one feels right? The correct answer is D. popliteal. D is correct because popliteal is the posterior regional term for the back of the knee. It appears on the posterior list alongside terms such as gluteal, sural, and calcaneal. A is wrong because patellar names the kneecap on the anterior surface. Using it would place the swelling on the wrong side of the joint. B is wrong because sural names the calf, the fleshy posterior region of the lower leg below the knee. It is close to the correct region but sits distal to it. C is wrong because crural names the leg or shin, the anterior region below the knee. It refers to the lower leg generally rather than to the knee hollow. Ordinary words like arm or leg are vague, so anatomy assigns each body surface region a precise Latin or Greek derived name with a fixed boundary, letting clinicians describe location without ambiguity. The biggest trap is that anterior and posterior names differ at the same joint. The knee is patellar in front but popliteal behind. The elbow is antecubital in front, and the lower leg is crural in front but sural behind. Test questions often describe the back of a structure specifically to check that you won't default to the more familiar anterior term. Every one of these terms maps directly onto structures named after it. The brachial artery runs through the brachial region. The femoral nerve serves the femoral region, and axillary lymph nodes sit in the axilla. So this vocabulary pays off repeatedly in later courses. Clinically, this precision matters immediately. Nurses draw blood at the antecubital region, check a popliteal pulse behind the knee, and chart pressure injuries at the sacral and calcaneal regions. Watch for overlap too, since lumbar, inguinal, and umbilical also name abdominopelvic regions. So a surface landmark calls for the regional term, while a grid of the abdomen calls for the abdominopelvic system. Master these regional names once, and you'll recognize them again in vessels, nerves, muscles, and bones throughout every course that follows. Question 16. A thoracic surgeon plans an approach to the esophagus and trachea, structures that lie in the central compartment of the chest between the two lungs, and that share the space with the heart and great vessels. Which region of the thoracic cavity contains these structures? Your options are A. Pleural cavity, B. Mediastinum, C. Pericardial cavity, D. Abdominal cavity. Got a guess? Lock it in. The correct answer is B. Mediastinum. B is correct because the mediastinum is the central compartment of the thoracic cavity, flanked by the two pleural cavities. It houses the heart, great vessels, trachea, esophagus, and thymus. A is wrong because each pleural cavity is a lateral space that encloses one lung. The trachea and esophagus lie between them rather than within them. C is wrong because the pericardial cavity sits inside the mediastinum but encloses only the heart. It does not contain the trachea or esophagus. D is wrong because the abdominal cavity lies inferior to the diaphragm and contains organs such as the stomach, liver, and intestines. It is outside the thoracic cavity entirely. Before a surgeon can operate, they need to know exactly which compartment an organ lives in. The chest is not one open space, it's a set of nested cavities, each with its own name and boundary. The diaphragm divides the ventral body cavity into thoracic above and abdominopelvic below. Within the thorax sit three spaces, two lateral pleural cavities, each enclosing one lung, and the mediastinum between them. The central compartment holding the heart, great vessels, trachea, esophagus, and thymus. The key is nesting, not a flat list. The pericardial cavity sits inside the mediastinum surrounding only the heart, while the mediastinum itself sits inside the thoracic cavity, flanked by the two separate pleural cavities. The esophagus lives in the mediastinum, outside the pericardial cavity and outside both pleural spaces. Clinical scenarios lean on these boundaries constantly. A pneumothorax collapses only one lung because the pleural cavities are separate. Cardiac tamponade is dangerous because the pericardial space is small and enclosed, and a mediastinal mass compresses the trachea or esophagus, producing breathing or swallowing trouble. The heart technically sits in both the mediastinum and the pericardial cavity, so the surrounding detail in a question decides which answer is meant. Trachea and esophagus nearby point to the mediastinum. Fluid pressing on the heart points to the pericardial cavity. Question 17. A patient with pericarditis has inflammation of the membrane surrounding the heart, and a friction rub is audible through the stethoscope. The physician explains that the roughened surfaces are rubbing during each heartbeat. Which membrane layer directly covers the outer surface of the heart itself? Your options are A. Visceral pericardium, B. Parietal pericardium, C. Visceral pleura, D. Parietal peritoneum. Which one is it? Pause the video if you need more time. The correct answer is A. Visceral pericardium. A is correct because the visceral layer of a serous membrane covers the outer surface of the organ within the cavity. For the heart, this layer is the visceral pericardium, also called the epicardium. B is wrong because the parietal pericardium lines the wall of the cavity and forms the outer sac. It faces the visceral layer across a thin film of serous fluid, but does not touch the heart surface. C is wrong because the visceral pleura is the correct type of layer but the wrong organ. It covers the surface of the lungs. D is wrong because the parietal peritoneum lines the wall of the abdominal cavity. It is both the wrong layer and the wrong body region. Press a fist into a partly inflated balloon. The wall wrapping your fist and the wall facing the room are the same sheet of rubber, folded back on itself with a thin space between the layers. That's exactly how every serous membrane wraps around an organ. And notice something important. The fist never actually enters the balloon's interior. Organs are never actually inside the serous cavity. They're wrapped by a membrane that folds around them, creating two layers with a thin space between. The parietal layer lines the wall of the cavity, and the visceral layer covers the organ itself. Between them sits a thin film of lubricating serous fluid, letting organs slide against cavity walls and each other with almost no friction as the lungs inflate, the heart beats, and the intestines move. 3 serous membranes are named for their locations. The pleura surrounds the lungs, the pericardium surrounds the heart, and the peritoneum surrounds the abdominal organs, each with its own parietal and visceral layer. Any layer touching an organ is visceral, and any layer lining a wall is parietal. That's all 6 terms generated without memorizing a single one separately. Lose the lubrication though, and the consequences are severe. Pleurisy causes sharp breathing pain. Pericarditis produces a friction rub. Peritonitis is life-threatening, and fluid buildup in the abdomen is called ascites. Question 18. An anatomy instructor asks, which 2 spaces together form the dorsal body cavity? Noting that these 2 spaces are continuous with one another and protects the organs of the nervous system. Which pair is correct? Your options are A. Thoracic and abdominopelvic cavities, B. Pleural and pericardial cavities, C. Cranial and vertebral cavities, D. Abdominal and pelvic cavities. Take a second. Which answer would you pick? The correct answer is C. Cranial and vertebral cavities. C is correct because the dorsal body cavity has exactly 2 subdivisions. The cranial cavity housing the brain and the vertebral cavity housing the spinal cord. Because the brain and spinal cord are continuous, so are these 2 spaces. A is wrong because the thoracic and abdominopelvic cavities are the 2 subdivisions of the ventral body cavity. Separated by the diaphragm, they house the viscera, not the central nervous system. B is wrong because The pleural and pericardial cavities are subdivisions within the thoracic cavity. They surround the lungs and heart respectively. D is wrong because the abdominal and pelvic cavities are the two continuous parts of the abdominopelvic cavity. They are ventral rather than dorsal. The body's internal spaces divide into two principal cavities, and the dorsal cavity is the smaller, simpler one. Tucked toward the back of the body, its entire job is protecting the nervous system. The dorsal cavity has just two subdivisions: the cranial cavity, enclosed by the skull and housing the brain, and the vertebral cavity, formed by the vertebral column and enclosing the spinal cord. Because the brain and spinal cord are physically continuous, these two spaces form one unbroken protected channel. Protection here is layered. Rigid bone forms the outer shell, while cerebrospinal fluid surrounds the brain and spinal cord as a fluid cushion, absorbing shocks that would otherwise strike neurons directly. This is the most heavily defended arrangement in the body, fitting since neurons largely don't regenerate. The dorsal and ventral cavities are not mirror images. The ventral cavity is larger, divided by the diaphragm, and lined throughout by serous membranes, while the dorsal cavity has only two subdivisions and no serous membranes at all. Expecting parietal and visceral layers around the brain is a costly mistake. Because the cranial and vertebral cavities are continuous, a lumbar puncture in the lower back can diagnose brain conditions, and meningitis is treated as a whole central nervous system emergency, not a local one. Question 19. A young adult arrives at the emergency department with sharp, localized pain in the lower right portion of the abdomen, and the physician immediately suspects appendicitis. Charting requires naming the region used in the 4-quadrant system. Which quadrant should be documented? Your options are A. Right upper quadrant, B. Left lower quadrant, C. Left upper quadrant, D. Right lower quadrant. Before I reveal it, which one do you think is right? The correct answer is D. Right lower quadrant. D is correct because the right lower quadrant contains the appendix along with the cecum and portions of the small intestine. Pain localized there is the classic presentation of appendicitis. A is wrong because the right upper quadrant contains most of the liver, the gallbladder, and part of the stomach. Pain there suggests hepatobiliary problems rather than appendicitis. B is wrong because the left lower quadrant contains the sigmoid colon and portions of the small and large intestine. The appendix is not located on the left side. C is wrong because the left upper quadrant contains the stomach, spleen, and pancreas. It sits diagonally opposite the appendix. When a patient points to their abdomen, a clinician needs to translate that spot into a list of likely organs, fast. That's the entire purpose of the 4-quadrant system. 2 lines intersect at the belly button, splitting the abdomen into 4 zones, the right upper, right lower, and left lower quadrants. 2 lines, 4 names, no ambiguity. That's exactly why this system dominates emergency settings. Each quadrant has a signature set of organs. The right upper quadrant houses the liver and gallbladder. The left upper holds the stomach and spleen. The right lower contains the appendix and cecum, and the left lower carries the sigmoid colon. One rule overrides everything. Right and left always refer to the patient's own right and left, never the observer's. Get this backwards and you might send someone looking for an inflamed appendix on the wrong side of the body. Quadrants exist for speed, 4 zones built for urgent reasoning before any test is run. The 9-region system trades that speed for anatomical precision, so exam stems mentioning epigastric or iliac areas have already shifted systems. Question 20. A patient describes burning discomfort in the central region of the upper abdomen, immediately superior to the umbilical region and flanked on both sides by the hypochondriac regions. The clinician documents the location using the 9-region system. Which region is being described? Your options are A. Umbilical, B. Epigastric, C. Hypogastric, D. Right hypochondriac. What's your answer? Commit to one before I continue. The correct answer is B. Epigastric. B is correct because the epigastric region is the central region of the superior row in the 9-region grid, sitting above the stomach and between the two hypochondriac regions. Its position immediately superior to the umbilical region confirms the identification. A is wrong because the umbilical region is the central region of the middle row, surrounding the navel. The described location lies directly above it. C is wrong because the hypogastric region, also called the pubic region, is the central region of the inferior row. It sits at the opposite end of the central column. D is wrong because the right hypochondriac region is one of the lateral regions of the superior row, beneath the cartilage of the ribs on the right. The description explicitly places the discomfort between the hypochondriac regions rather than in one of them. The 9-region system comes from 4 planes, not 2 lines. 2 vertical planes drop from the midpoint of each clavicle, and 2 horizontal planes cross the abdomen, one below the ribs and one across the top of the hip bones. Together they form a tic-tac-toe grid of 3 rows and 3 columns. The central column, running top to bottom, is epigastric, umbilical, and hypogastric. The flanking columns repeat left and right. Hypochondriac in the top row, lumbar in the middle row, and iliac, also called inguinal, in the bottom row. None of these names are arbitrary. Hypochondriac means below the cartilage. Epigastric means over the stomach. Hypogastric means below the stomach. Lumbar refers to the loin, and iliac refers to the ilium. Learn the meaning and the position comes for free. Anatomists use 9 regions for precision, while clinicians use 4 quadrants for speed, and both correctly describe the same anatomy. Epigastric pain shows why the finer grid matters, since that single region overlies the esophagus, stomach, pancreas, liver, and even referred cardiac pain. Watch for lumbar, inguinal, and umbilical, since these terms appear in both vocabularies. A stem describing a 4-plane grid wants the 9-region system, while a stem naming one surface landmark wants the regional term. Question 21. A laboratory report describes a neutral atom containing 8 protons, 8 neutrons, and 8 electrons. A student must extract the 2 numbers that chemists use to describe any atom. Which statement about this atom is correct? Your options are A. Its atomic number is 8 and its mass number is 16. B. Its atomic number is 16 and its mass number is 8. C. Its atomic number is 8 and its mass number is 24. D. Its atomic number is 16 and its mass number is 16. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is A. Its atomic number is 8 and its mass number is 16. A is correct because the atomic number equals the proton count, which is 8, and identifies the atom as oxygen. The mass number equals protons plus neutrons, giving 8 plus 8 or 16. B is wrong because this reverses the 2 values. The atomic number can never be the larger figure, because mass number always includes the protons plus any neutrons present. C is wrong because this adds the electrons into the mass number. Electrons weigh roughly 1/2000th of a proton, so they are excluded from mass number entirely. D is wrong because this treats the atomic number as the sum of protons and neutrons. Atomic number counts protons alone and is what defines the element. Every atom carries 2 numbers because identity and mass are separate properties. Keeping them straight is the foundation for understanding isotopes, radioactive traces, and the periodic table itself. Protons carry positive charge, neutrons carry no charge. and both weigh about 1 atomic mass unit sitting in the nucleus. Electrons carry negative charge but weigh almost nothing, occupying shells around the nucleus, which is why the nucleus holds nearly all the mass in almost none of the volume. The atomic number equals the number of protons and defines the element itself. Every atom with 6 protons is carbon. The mass number equals protons plus neutrons, deliberately excluding electrons since their weight is negligible. So carbon with 6 protons and 6 neutrons has a mass number of 12. One recurring error is folding electrons into the mass number, which inflates the figure and shows the exclusion was never understood. A second error is reversing the two numbers, producing an atomic number larger than the mass number, which is arithmetically impossible since mass number always includes every proton plus any neutrons. The number most easily confused with these two is atomic weight, the abundance weighted average of all naturally occurring isotopes, which is why periodic table entries are rarely whole numbers. Mass number describes one particular atom. Atomic weight describes the element as it occurs in nature. Question 22. A nuclear medicine researcher works with carbon-14 while the carbon in ordinary body tissue is almost entirely carbon-12. The two forms behave identically in every chemical reaction the researcher runs, differing only in mass. What accounts for the difference between them? Your options are: A. They contain different numbers of protons, which changes their chemical identity. B. They contain different numbers of electrons, which changes their bonding behavior. C. They contain different numbers of protons and electrons, but the same number of neutrons. D. They contain the same number of protons, but different numbers of neutrons. Which would you go with? Lock it in before the reveal. The correct answer is D. They contain the same number of protons but different numbers of neutrons. D is correct because isotopes of an element share the same proton number and therefore the same electron number, differing only in neutron count. Because chemical behavior depends on electrons, isotopes react identically and differ only in mass. A is wrong because a change in proton number would change the element itself. An atom with a different proton count would no longer be carbon. B is wrong because a change in electron number produces an ion, not an isotope, and would change how the atom bonds. The scenario specifically states that chemical behavior is identical. C is wrong because this describes ions of different elements rather than isotopes. Isotopes hold protons and electrons constant and vary neutrons. Radioactive iodine lights up the thyroid because the gland cannot tell it apart from ordinary iodine. To see why, we need to understand what an isotope actually is. Isotopes are atoms of the same element with the same number of protons but different numbers of neutrons. Carbon 12, 13, and 14 all have 6 protons and 6 electrons. Only the neutron count and therefore the mass changes. Chemical behavior depends on electrons, and isotopes have identical electron configurations because their proton counts match. That's why an enzyme or transport protein can't tell them apart, and why the thyroid concentrates radioactive iodine just as eagerly as the ordinary kind. Guard this distinction carefully. An isotope has an altered neutron count, keeping the same charge and chemistry but a different mass. An ion has an altered electron count, giving it a net charge and different chemistry, but essentially the same mass. This is why the thyroid scan works. Radioactive iodine is pulled into the gland exactly like ordinary iodine, because only the nucleus differs. The same principle lets PET scans tag glucose to reveal tumors and active brain regions without changing how the body uses it. Question 23. An instructor points out that neon has a completely filled outer electron shell and does not readily participate in chemical reactions, while sodium and chlorine react vigorously. Which principle best explains neon's lack of reactivity? Your options are A. Atoms with more protons than electrons resist reacting because of their net positive charge. B. Atoms are chemically stable when their valence shell is full, so they have no tendency to gain, lose, or share electrons. C. Atoms whose first shell holds 8 electrons are inert, while atoms with fewer are reactive. D. Atoms become inert when their mass number is exactly double their atomic number. Don't overthink it. Which one feels right? The correct answer is B. Atoms are chemically stable when their valence shell is full, so they have no tendency to gain, lose, or share electrons. B is correct because the valence shell is the outermost occupied electron shell, and a full valence shell leaves an atom with no driving force to bond. This is the core idea behind the octet rule and explains why the noble gases are unreactive. A is wrong because neutral atoms have equal numbers of protons and electrons by definition. An imbalance would make the particle an ion rather than a stable neutral atom. C is wrong because the first shell holds a maximum of 2 electrons, not 8. The 8 electron figure applies to the second and third shells. D is wrong because mass number reflects protons plus neutrons and has no bearing on chemical reactivity. Reactivity is governed entirely by the arrangement of valence electrons. Why do some atoms explode on contact while others sit inert for centuries? The answer lies entirely in the arrangement of electrons in the outermost shell, and it's the single most useful predictive idea in basic chemistry. Electrons fill shells around the nucleus starting closest in because those spots are lowest energy. The first shell holds 2 electrons. The second and third each hold 8, and whichever shell is outermost is called the valence shell, home to the only electrons that participate in bonding. Atoms with just 1 or 2 valence electrons, like sodium, find it easier to give them away, becoming positive. Atoms needing just 1 or 2, like chlorine, tend to grab them, becoming negative. Carbon sits halfway with 4 valence electrons, so it shares, forming 4 covalent bonds that anchor the molecules of life. The most commonly misremembered detail, the first shell holds only 2 electrons, not 8. Helium is stable with exactly 2, while hydrogen needs just 1 more, which is why it forms exactly 1 bond and appears in nearly every organic molecule. Oxygen, carbon, hydrogen, and nitrogen dominate biology because their valence configurations make them versatile bonding partners, not because they're abundant. And when a question tests this, remember, atomic number counts all the electrons, but valence counts only the outermost ones. And it's valence that decides reactivity. Question 24. A patient with a fever several degrees above normal becomes confused. The physician explains that excess heat has disrupted the weak attractions holding enzymes in their functional 3-dimensional shapes. The same weak attractions hold the 2 strands of the DNA double helix together and give water its surface tension. Which type of bond is being described? Your options are A. Ionic bond, B. Nonpolar covalent bond, C. Hydrogen bond, D. Polar covalent bond. Got a guess? Lock it in. The correct answer is C. Hydrogen bond. C is correct because hydrogen bonds are weak attractions between a slightly positive hydrogen of one polar molecule and a slightly negative atom of another. Individually fragile but collectively powerful, they maintain protein shape, hold DNA strands together, and produce water surface tension. A is wrong because ionic bonds form when electrons are completely transferred and oppositely charged ions attract. They are considerably stronger than the attractions described and are weakened by water rather than by modest heat. B is wrong because nonpolar covalent bonds involve equal sharing of an electron pair and are strong. They hold atoms together within molecules such as oxygen gas and dominate the interior of fats. D is wrong because polar covalent bonds involve unequal sharing and are also strong bonds within a molecule. They create the charge imbalance that makes hydrogen bonding possible, but are not themselves the weak attraction described. When a fever climbs high enough to cause confusion, the cause isn't mysterious at all. It's chemical. Heat is breaking the weakest attractions, holding proteins into their working shapes, and those attractions are hydrogen bonds. A hydrogen bond isn't like a covalent bond that locks atoms together inside a molecule. It's a weak electrostatic pull between a slightly positive hydrogen on one polar molecule and a slightly negative oxygen or nitrogen on another. 3 of the body's most important structures depend on these weak attractions: water's cohesion and heat capacity, the base pairing that holds DNA's 2 strands together, and the alpha helices and beta sheets that give proteins their shape. The attraction exists because of polar covalent bonding one level down. Oxygen pulls shared electrons closer, leaving it slightly negative and hydrogen slightly positive. A polar covalent bond joins hydrogen to oxygen inside one water molecule, while a hydrogen bond attracts that molecule to its neighbor. This weakness is the design, not a flaw. It lets DNA unzip for replication, and enzymes flex around their substrates. But a high fever breaks hydrogen bonds faster than they reform, unfolding proteins across countless enzymes at once, which is why extreme fever causes widespread confusion rather than one isolated symptom. Question 25. Sodium has a single electron in its valence shell, and chlorine needs 1 electron to complete its own. When the 2 meet, sodium surrenders its electron to chlorine, and the resulting charged particles are drawn together by electrostatic attraction. Which choice correctly names the bond and the 2 particles? Your options are A. An ionic bond, and the particles are a cation and an anion. B. A polar covalent bond, and the particles are dipoles. C. A non-polar covalent bond, and the particles are isotopes. D. A hydrogen bond, and the particles are electrolytes. Which one is it? Pause the video if you need more time. The correct answer is A. An ionic bond, and the particles are a cation and an anion. A is correct because complete transfer of an electron defines an ionic bond. The atom that loses an electron becomes a positively charged cation, and the atom that gains one becomes a negatively charged anion, and their opposite charges hold them together. B is wrong because a polar covalent bond involves unequal sharing rather than transfer, and the resulting molecule carries only partial charges. Dipoles are molecules with uneven charge distribution, not fully charged particles. C is wrong because nonpolar covalent bonding means equal sharing, which produces no charged particles at all. Isotopes are variants of an element that differ in neutron number and have nothing to do with bonding. D is wrong because a hydrogen bond is a weak attraction between molecules rather than a transfer of electrons. Electrolytes are substances that ionize in solution and conduct current, which describes a property rather than the particles formed by this transfer. Sodium has 1 electron to give away, and chlorine has 1 empty spot to fill. What happens between them is not sharing at all, but a complete handoff of an electron from one atom to the other. An atom that loses electrons becomes a positively charged cation, while one that gains electrons becomes a negatively charged anion. A handy trick is that the T in cation looks like a plus sign. Once these charges form, electrostatic attraction between them is what we call the ionic bond. Sodium chloride does not form individual molecules. Instead, sodium and chloride ions stack into a repeating crystal lattice, alternating positive and negative charges held together by attraction throughout the entire structure. Because the body is mostly water, ionic compounds dissociate completely into free ions called electrolytes. Sodium and potassium drive nerve impulses. Calcium triggers muscle contraction and clotting. And bicarbonate and phosphate manage acid-base balance. Remember, complete electron transfer creates full charges and ionic bonds, while unequal sharing in polar covalent bonds only creates partial charges. That distinction is exactly why abnormal electrolyte levels can disrupt the heart's electrical rhythm badly enough to be fatal. Question 26. During a prolonged fast, the liver breaks stored glycogen down into individual glucose molecules and releases them into the blood. Bonds are broken during this process and energy is liberated. Which choice correctly names the reaction pattern and its metabolic role? Your options are A synthesis reaction, and it is anabolic. B, a decomposition reaction, and it is catabolic. C, an exchange reaction, and it is anabolic. D, a decomposition reaction, and it is anabolic. Take a second. Which answer would you pick? The correct answer is B, a decomposition reaction, and it is catabolic. B is correct because decomposition reactions split a larger molecule into smaller ones, following the pattern in which bonds are broken and energy is released. Because breakdown reactions release stored energy, they constitute catabolism. A is wrong because synthesis reactions join smaller reactants into larger products and store energy in the new bonds. Glycogen breakdown is the reverse of that process. C is wrong because exchange reactions shuffle parts between reactant molecules, breaking and forming bonds simultaneously. Glycogen breakdown produces only smaller pieces of the original molecule with nothing swapped in. D is wrong because the reaction pattern is correctly identified, but anabolism refers to building rather than breaking down. Decomposition reactions are catabolic by definition. Nearly every reaction in the body, from liver glycogen breakdown to glucose storage, follows one of three basic patterns. Learning these patterns matters more than memorizing individual reactions, because the pattern itself predicts how energy flows. Synthesis reaction combine reactants into a larger product, forming bonds and absorbing energy. Decomposition reactions break a larger molecule apart, releasing the energy stored in those bonds. Exchange reactions do both at once, breaking some bonds and forming others so components are shuffled between molecules. A key physiological example of exchange is the first step of glucose breakdown, where a phosphate group transfers from ATP directly onto glucose. Nothing is built from scratch and nothing is fully torn apart. A component simply moves from one molecule to another. Reaction rate depends on a handful of factors: higher temperature, higher reactant concentration, smaller particle size, and catalyst. Catalysts matter most, because enzymes lower activation energy and metabolic reactions run fast at body temperature, making enzyme availability the true regulator of biological reaction rates. Two things becoming one signal synthesis, one thing becoming two signals decomposition, and parts trading places signals exchange. A double arrow or equal forward and reverse rates points to equilibrium, a dynamic balance where both directions continue at full speed. Question 27. A construction worker sweating heavily in summer heat cools down as the perspiration evaporates from the skin surface. The instructor explains that a large quantity of heat is carried away with each gram of water that turns to vapor. Which property of water accounts for this cooling effect? Your options are A, high heat capacity, B, solvent properties arising from polarity, C, cushioning ability, D, high heat of vaporization. Before I reveal it, which one do you think is right? The correct answer is D, high heat of vaporization. D is correct because high heat of vaporization means a great deal of heat must be absorbed to convert liquid water into vapor. Sweating exploits this directly since the heat needed for evaporation is drawn from the body surface. A is wrong because high heat capacity describes water's ability to absorb heat with little temperature change of its own, buffering the body against sudden thermal swings. It stabilizes temperature but does not remove heat from the body. B is wrong because solvent properties allow water to dissolve and transport solutes throughout the body. Dissolving power plays no role in the evaporative cooling described. C is wrong because cushioning refers to water resisting compression and protecting delicate structures, as cerebrospinal fluid protects the brain. It is a mechanical property rather than a thermal one. Water makes up more than half of an adult's body weight, and nearly every remarkable thing it does traces back to one fact. It's a polar molecule that forms hydrogen bonds with other water molecules. Every property we're about to cover is just a consequence of that. 5 properties matter here, and exam questions constantly swap them. High heat capacity stabilizes temperature. High heat of vaporization cools the body through sweat. Water acts as a universal solvent for dissolving and transporting substances, as a chemical reactant in hydrolysis and dehydration synthesis, and as a cushion that resists compression. Heat capacity means water absorbs heat without its own temperature swinging much, acting like an internal thermostat during exercise or fever. Heat of vaporization is different. It's the large amount of heat carried away when sweat converts from liquid to vapor, which is exactly why sweating cools you down. Because water is polar, it surrounds charged and polar particles and keeps them dispersed, making it the universal solvent that carries nutrients, gases, and waste through blood and tissue fluid. But water isn't just a backdrop for chemistry. In hydrolysis, it's added to split molecules apart for digestion. And in dehydration synthesis, it's removed as smaller molecules join to build proteins, glycogen, and fat. On exams, identify the property by what water is doing in the sentence. Absorbing heat without changing temperature is heat capacity. Evaporating to carry heat away is heat of vaporization. Dissolving or transporting is solvent behavior. Splitting or joining molecules is chemical reactivity. And protecting from impact is cushioning. Remember the 2 clinical bookends too. Dehydration concentrates the blood and impairs cooling, while water intoxication dilutes electrolytes and swells cells, including in the brain. Question 28. A tube of freshly drawn whole blood is left standing undisturbed on a laboratory bench. Within an hour, the cells have settled to the bottom, leaving a straw-colored fluid above them. Which type of mixture does whole blood represent, and why? Your options are A solution, because its solid particles are ions small enough that they never settle. B, a colloid, because its particles scatter light, but remain permanently dispersed. C, a suspension, because its particles are large enough to settle out when left undisturbed. D, a compound, because its components are held together by chemical bonds. What's your answer? Commit to one before I continue. The correct answer is C. A suspension, because its particles are large enough to settle out when left undisturbed. C is correct because a suspension contains particles large enough to be visible and heavy enough to settle out when the mixture is left standing. Blood cells stay dispersed only because circulation keeps the blood in constant motion. A is wrong because solutions contain solid particles so small that they never settle, and the mixture stays transparent. Saline and dissolved glucose fit that description, but visible cells do not. B is wrong because colloids contain larger particles that scatter light and give a cloudy appearance but still do not settle. The cytosol of a cell and the plasma proteins are colloids while whole blood settles. D is wrong because a compound has atoms joined by chemical bonds and cannot be separated by physical means. Blood components separate under gravity alone, which is the signature of a mixture. 3 tubes, 3 behaviors. One stays clear, one stays cloudy, and one separates into layers. The difference between them comes down to a single variable, the size of the dispersed particles. A mixture combines substances physically without chemical bonding, so each part keeps its own properties and can be separated by physical means, like centrifuging blood into layers. A compound is different. Its atoms are chemically joined, so no physical process can separate them. The way water can't be spun apart into hydrogen and oxygen. Picture 3 tubes side by side. The solution stays perfectly clear because its particles are too small to ever settle. The colloid stays uniformly cloudy because larger particles scatter light but still don't settle. The suspension separates because its particles are large and heavy enough for gravity to pull them down. Rather than memorizing particle sizes, use the settling test. Never settles and transparent means solution. Never settles and cloudy means colloid. Settles out means suspension. And this is exactly why the standing tube, not appearance alone, is the reliable clue. The trap is assuming cloudy always means suspension. Cloudiness only tells solutions apart from colloids. It's settling that tells colloids apart from suspensions. Question 29. A student compares two laboratory solutions, one measured at a pH of 5 and the other at a pH of 7. The instructor emphasizes that the pH scale is logarithmic rather than linear. Which statement about these two solutions is accurate? Your options are: A. The pH 5 solution has twice the hydrogen ion concentration of the pH 7 solution. B. The pH 5 solution has 100 times the hydrogen ion concentration of the pH 7 solution. C. The pH 7 solution has 10 times the hydrogen ion concentration of the pH 5 solution. D. The two solutions differ only in hydroxide ion concentration, since pH measures hydroxide directly. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is B. The pH 5 solution has 100 times the hydrogen ion concentration of the pH 7 solution. B is correct because each whole number step on the pH scale represents a tenfold change in hydrogen ion concentration. 2 steps, therefore, represent a 100-fold difference, and the lower pH is the more concentrated in hydrogen ions. A is wrong because a 2-fold difference would describe a linear scale. The defining feature of pH is that it compresses a 100-fold difference into 2 units. C is wrong because this inverts the relationship. As hydrogen ion concentration rises, pH falls, so the pH 5 solution is the more acidic of the two. D is wrong because the pH scale measures hydrogen ion concentration. Hydroxide concentration moves inversely with it, but is not what the number reports. The pH scale runs backward from what intuition expects. As hydrogen ion concentration rises, pH falls. So a solution becoming more acidic produces a smaller number, not a larger one. The scale runs from 0 to 14. A pH of 7 is neutral, like pure water. Below 7 is acidic and above 7 is basic, or alkaline, with the extremes marking greater intensity in each direction. The scale is logarithmic, not linear. Each whole number step represents a tenfold change in hydrogen ion concentration, which is why even small pH shifts in the body represent enormous changes in acidity. Body fluids sit at very different points on this scale. Gastric juice is strongly acidic to digest proteins. Urine varies around slightly acidic, saliva sits near neutral. And pancreatic juice is basic enough to neutralize incoming stomach acid. Arterial blood is held between 7.35 and 7.45, defended more tightly than almost any other body variable. This is because protein shape, including enzyme shape, depends on hydrogen bonding sensitive to pH. So a shift in pH degrades metabolism broadly by disrupting enzymes everywhere at once. Question 30. A patient in diabetic ketoacidosis is accumulating acidic ketone bodies in the blood, yet arterial pH has fallen only slightly so far. The physician credits the bicarbonate system in the plasma for holding the line. What does this chemical system do? Your options are: A. It resists pH change by binding hydrogen ions when pH falls and releasing them when pH rises. B. It permanently removes hydrogen ions from the body by excreting them into the urine. C. It converts weak acids into strong acids so that they dissociate completely and are cleared faster. D. It drives blood pH above 7.45 to counterbalance the accumulating acid. Which would you go with? Lock it in before the reveal. The correct answer is A. It resists pH change by binding hydrogen ions when pH falls and releasing them when pH rises. A is correct because A buffer minimizes pH change by acting in both directions, soaking up excess hydrogen ions when a solution becomes too acidic and donating them when it becomes too basic. In the blood, bicarbonate binds the excess acid, while carbonic acid supplies hydrogen ions when needed. B is wrong because excretion of hydrogen ions into urine is a kidney function that works over hours to days. Buffers act chemically and within seconds, and they do not remove anything from the body. C is wrong because buffers do the reverse, converting strong acids and bases into weak ones that dissociate only partially. Complete dissociation is precisely what makes strong acids dangerous to pH. D is wrong because pushing pH above 7.45 would produce alkalosis, which is itself a dangerous state. A buffer defends the normal range rather than overshooting it. Blood pH must stay within an incredibly narrow window. Even though metabolism constantly produces acid from carbon dioxide, lactic acid, and ketone bodies. Something must neutralize this acid load within seconds, and that job belongs to buffer systems. A true buffer resists pH change in both directions. When the blood turns too acidic, it binds free hydrogen ions like a base, and when it turns too basic, it releases hydrogen ions like an acid. This bidirectional action is what separates a real buffer from a simple acid or base. The most important blood buffer is the bicarbonate system, a pair of carbonic acid and bicarbonate ion. Excess acid is bound by bicarbonate and converted into a weak acid, while excess base is met by carbonic acid releasing hydrogen ions. And this conversion of strong acids and bases into weak ones is the core mechanism behind all buffering. Buffers alone aren't enough, since they only convert acid into a less damaging form without removing it. The lungs are just breathing within minutes to blow off carbon dioxide, and only the kidneys, acting over hours to days, actually excrete hydrogen ions and eliminate acid from the body. When a stem describes something happening instantly in the plasma, it wants a buffer. When it describes hydrogen ions appearing in the urine, it wants the kidney, the only tier that truly removes acid from the body. Question 31. An endurance athlete depletes the carbohydrate reserves held in the liver and skeletal muscle during a long race. A coach explains that this reserve is a branched polymer of glucose that the body can dismantle quickly when blood sugar starts to fall. Which molecule is being described? Your options are starch, B. cellulose, C. sucrose, D. glycogen. Don't overthink it. Which one feels right? The correct answer is D. Glycogen. D is correct because glycogen is the storage polysaccharide of animals, stockpiled chiefly in liver and skeletal muscle. It is broken down rapidly into glucose whenever the body needs fuel. Is wrong because starch is the storage polysaccharide of plants and the main dietary carbohydrate humans eat. The body digests it but does not store carbohydrate in that form. B is wrong because cellulose is a structural polysaccharide of plants that humans cannot digest at all. It passes through as dietary fiber rather than serving as an energy reserve. C is wrong because sucrose is a disaccharide of glucose and fructose, familiar as table sugar. Disaccharides are far too small to serve as a bulk storage reserve. When an endurance athlete suddenly hits the wall, it's not fatigue building gradually, it's glycogen, the body's stored carbohydrate, running out entirely. To understand why that failure is so abrupt, we need to understand how carbohydrates are built and stored in the first place. Carbohydrates are organic molecules whose main job is fuel. The brain runs on glucose almost exclusively, which is why blood glucose is guarded so tightly, and it's also why carbohydrates are classified into 3 size-based groups. Monosaccharides are single sugar units like glucose, fructose, and galactose. Disaccharides form when 2 of these join together, like sucrose, lactose, and maltose, and notably, they must be broken back down before they can cross the intestinal wall, which is exactly what fails in lactose intolerance. Polysaccharides are long chains of hundreds or thousands of glucose units, including starch, glycogen, and cellulose. The reason glycogen is stored as one giant branched polymer rather than loose glucose comes down to osmosis. Thousands of free glucose molecules would each pull water into the cell, but linked together into a single branched molecule. They exert the pull of just one particle, letting the cell stockpile fuel without flooding itself. Glucose is the circulating fuel, glycogen is the stored form, and the liver converts between them continuously. When glycogen runs dry, that continuous conversion stops working, and that's the wall an endurance athlete hits. Question 32. A student asks why phospholipids placed in water spontaneously organize themselves into a double layer with the tails facing inward, while triglycerides simply clump into droplets. Which structural property of phospholipids explains the difference? Your options are: A. Phospholipids are entirely hydrophobic, so they exclude water from both surfaces equally. B. Phospholipids carry a full negative charge that repels neighboring molecules into a flat sheet. C. Phospholipids are amphipathic, having a hydrophilic phosphate head and 2 hydrophobic fatty acid tails. D. Phospholipids are built from 4 interlocking hydrocarbon rings that stack naturally into layers. Got a guess? Lock it in. The correct answer is C. Phospholipids are amphipathic, having a hydrophilic phosphate head and 2 hydrophobic fatty acid tails. C is correct because a phospholipid has one of its 3 fatty acids replaced by a phosphate-containing group, giving it a water-loving head and 2 water-faring tails. In water, this dual nature forces the heads outward towards the fluid and the tails inward, producing the bilayer. A is wrong because if phospholipids were entirely hydrophobic, they would behave like triglycerides and form droplets. The water-loving head is precisely what distinguishes them. B is wrong because mutual repulsion would scatter the molecules rather than organize them into a stable sheet. The bilayer forms because of attraction between the heads and water, not repulsion among the phospholipids. D is wrong because 4 interlocking hydrocarbon rings describe the structure of steroids such as cholesterol. Cholesterol wedges into the bilayer to regulate fluidity but does not form the bilayer itself. Lipids are the odd class among organic molecules. They aren't defined by a shared structure, but by a shared behavior. Every lipid is hydrophobic, insoluble in water, yet dissolves easily in other lipids and organic solvents. Beyond that one property, their structures diverge wildly, giving us fats, membranes, hormones, and signaling molecules all under one label. Phospholipids are amphipathic with a charged water-loving phosphate head and 2 water-faring fatty acid tails. Dropped into water, there's only one arrangement that satisfies both ends: a bilayer, heads out, tails tucked safely inside. No enzyme builds this and no energy is spent. The geometry of the molecule alone makes it inevitable, and that spontaneous ordering underlies every membrane in the body. Exam stems identify lipid classes by structure or function. Glycerol bonded to 3 fatty acids is a triglyceride, the body's most concentrated energy store. A phosphate head with 2 tails is a phospholipid. 4 fused rings signal a steroid like cholesterol, the source of estrogen testosterone, cortisol, and vitamin D. A local signaling molecule tied to inflammation, pain, and fever is an eicosanoid, like the prostaglandins that aspirin and ibuprofen block. Fatty acid chains differ in one key structural detail. Saturated chains hold only single bonds, are packed with hydrogen, and packed tightly together, staying solid at room temperature. Unsaturated chains contain a double bond that puts a kink in the chain, so they can't pack tightly and they stay liquid instead. Cholesterol itself isn't the villain it's made out to be, since without it the body could build no membrane and no steroid hormone. What actually determines cardiovascular risk is how it's packaged for transport. LDL deposits cholesterol into artery walls, promoting plaque, while HDL carries it back to the liver for disposal. Question 33. Hemoglobin is assembled from 4 separate polypeptide chains that fit together into one functional oxygen-carrying molecule. A student must name the level of protein structure that describes how those separate chains are arranged relative to one another. Which level applies? Your options are A. Quaternary structure, B. Tertiary structure, C. Secondary structure, D. Primary structure. Which one is it? Pause the video if you need more time. The correct answer is A. Quaternary structure. A is correct because quaternary structure exists only in proteins built from 2 or more polypeptide chains and describes how those subunits fit together. Hemoglobin with its 4 subunits is the standard example. B is wrong because tertiary structure describes the overall 3-dimensional folding of a single polypeptide chain driven by interactions among its R groups. It stops at the boundary of one chain. C is wrong because secondary structure refers to local coiling into an alpha helix or folding into a beta pleated sheet produced by hydrogen bonds along the polypeptide backbone. It describes a segment rather than an assembly. D is wrong because primary structure is the linear sequence of amino acids joined by peptide bonds. It determines everything that follows but says nothing about subunit arrangement. Protein function depends entirely on shape, and shape is built up in 4 levels of increasing complexity. Each level is created by a different kind of chemical interaction, and knowing which interaction builds which level is the key to mastering this topic. Every amino acid shares the same core structure, but the variable R group gives each one its unique chemical personality, whether charged, polar, or hydrophobic. Amino acids link together through peptide bonds formed by dehydration synthesis to build the protein chain. Primary structure is just the amino acid sequence dictated by the gene, and a single error here, as in sickle cell disease, can distort the entire protein. Secondary structure forms from hydrogen bonds along the backbone, creating helices or sheets, while tertiary structure comes from R group interactions folding the whole chain into its final shape. Quaternary structure only appears when multiple separate chains, like hemoglobin's 4 subunits, fit together. Picture the chain first as a straight sequence, then coiling into helices and sheets, then folding into a compact globular unit, and finally, only for some proteins, joining with other folded chains like hemoglobin's 4 subunits. Proteins also fall into 2 broad categories. Fibrous proteins like collagen, keratin, and elastin are strand-like structural cables built for strength. Globular proteins like enzymes, antibodies, and hemoglobin are compact, soluble, and chemically active, the body's working machinery. Question 34. A laboratory technician accidentally heats an enzyme solution far above body temperature. After the solution cools back to normal, the enzyme still fails to catalyze its reaction. Which explanation accounts for the permanent loss of activity? Your options are A. The enzyme was consumed during the reaction and must be resupplied. B. The enzyme was denatured because heat disrupted the bonds maintaining its folded shape and destroyed the active site. C. The enzyme's primary structure was rewritten, changing the order of its amino acids. D. The enzyme's activation energy rose, so the reaction now requires more energy to begin. Take a second, which answer would you pick? The correct answer is B. The enzyme was denatured because heat disrupted the bonds maintaining its folded shape and destroyed the active site. B is correct because protein function depends on precise three-dimensional shape, which is held largely by fragile hydrogen bonds. Excess heat breaks those bonds, unfolds the protein, and destroys the active site, and the damage is frequently irreversible. A is wrong because catalysts are not consumed or permanently altered by the reactions they speed up. An enzyme emerges from each reaction ready to work again. C is wrong because primary structure is determined by the gene that codes for the protein and is not altered by heat. Denaturation unfolds the chain without changing the sequence of amino acids in it. D is wrong because activation energy is a property of the reaction, not something an enzyme can raise. The enzyme's job is to lower it, and a damaged enzyme simply fails to do so. An egg white turns from clear liquid to opaque solid in a hot pan, and it never turns back. Nothing chemical was added or removed. The protein molecule simply unfolded, and that unfolding was permanent. This everyday transformation is called denaturation. Denaturation is the loss of a protein's three-dimensional shape and with it its function. The weak hydrogen bonds holding that shape together break, but the covalent peptide backbone stays intact, so the amino acid sequence survives unchanged. That's exactly why denaturation is fundamentally different from mutation, which alters the sequence itself. Two agents cause most physiological denaturation. Excessive heat supplies thermal energy that breaks weak bonds faster than they can reform, while abnormal pH changes the charges on side chains, so attracting groups begin repelling instead. Both attack the same weak interactions from different directions, which is why the body defends temperature and pH so fiercely. Picture the folded protein held together by fragile hydrogen bonds along its backbone. Add heat, and those weak bonds snap while the peptide backbone itself never breaks, leaving an unfolded chain with the exact same sequence it started with. Severe denaturation, like a cooked egg, cannot reverse, while mild unfolding sometimes can. The body even uses this deliberately. Stomach acid denatures dietary proteins, so digestive enzymes can reach them. Remember the discriminator. Denaturation changes shape and leaves sequence intact, while mutation changes sequence itself. Question 35. The intestinal enzyme sucrase readily digests sucrose but has no effect whatsoever on lactose, even though both are disaccharides of similar size. A different enzyme, lactase, is required for lactose. Which property of enzymes explains this behavior? Your options are: A. Enzymes are consumed by their reactions, so each one can act only once before a new enzyme is needed. B. Enzymes supply the activation energy that a reaction requires in order to proceed. C. Each enzyme has an active site whose shape accommodates only a specific substrate. D. Enzymes function only in solutions with a pH below 7, and lactose is digested at a higher pH. Before I reveal it, which one do you think is right? The correct answer is C. Each enzyme has an active site whose shape accommodates only a specific substrate. C is correct because enzyme specificity arises from the shape of the active site, the pocket where substrates bind. Because only a molecule with a complementary shape fits, sucrase recognizes sucrose and ignores lactose entirely. A is wrong because enzymes emerge unchanged from the reactions they catalyze and are used repeatedly. If they were consumed, specificity would still not be explained. B is wrong because enzymes lower activation energy rather than supply it. They accelerate a reaction by making the barrier smaller, not by pushing energy into the reactants. D is wrong because enzymes each have an optimal pH, and many work best near neutral or even alkaline conditions, such as pancreatic enzymes in the small intestine. Optimal pH does not determine which substrate an enzyme recognizes. Sucrase acts only on sucrose and lactase acts only on lactose, even though the two sugars are nearly identical in size. This isn't a limitation, it's exactly why a cell can control which of its thousands of possible reactions actually happen. Enzymes are globular proteins acting as biological catalysts, speeding reactions without being consumed. They're essential because 37 degrees Celsius is too mild for most metabolic reactions to run fast enough, and heating the body to compensate would denature its proteins. Instead, enzymes lower the activation energy, the barrier a reaction must cross to begin. The enzyme binds its substrate at a pocket called the active site, holding it in the right orientation and straining its bonds. The classic lock and key image is slightly wrong. It's really induced fit, where the active site molds itself around the substrate, which is what allows it to strain those bonds. Because enzymes are proteins, each has its own temperature and pH optimum, like pepsin thriving in the acidic stomach, while pancreatic enzymes need the alkaline small intestine. Many also need non-protein helpers, cofactors, usually metal ions, and coenzymes, usually derived from vitamins, which is why a single vitamin deficiency can shut down an entire pathway. Enzyme names usually end in ase and reflect their substrate, like sucrose acting on sucrose. Exam questions test whether you know the enzyme is always the catalyst and the substrate is always what it acts on. Question 36. A student is asked to summarize how RNA differs structurally from DNA, covering strand arrangement, sugar, and the set of nitrogenous bases used. Which combination correctly describes RNA? Your options are A. Double-stranded, containing deoxyribose using thymine. B. Single-stranded, containing deoxyribose using uracil. C. Double-stranded, containing ribose using uracil. D. Single-stranded, containing ribose using uracil. What's your answer? Commit to one before I continue. The correct answer is D. Single-stranded, containing ribose using uracil. D is correct because RNA differs from DNA in exactly 3 ways. It is usually single-stranded rather than a double helix. Its pentose sugar is ribose rather than deoxyribose, and it substitutes uracil for thymine so that adenine pairs with uracil. A is wrong because this describes DNA rather than RNA. Double strands, deoxyribose and thymine are the 3 DNA features. B is wrong because the strand count and base are right for RNA, but deoxyribose belongs to DNA. The sugar difference is what the 2 names actually refer to. C is wrong because ribose and uracil are correct for RNA, but RNA is normally single-stranded. Only DNA forms the double helix. 2 nucleic acids exist because storage and delivery are different jobs. Genetic information must be preserved intact and copied faithfully, which calls for a stable, protected molecule. It must also be constantly read and delivered to where proteins are built, which calls for a disposable working copy. Both DNA and RNA are polymers of nucleotides, and every nucleotide has 3 parts: a pentose sugar, a phosphate group, and a nitrogen-containing base. The sugar and phosphate link into a backbone while the bases project inward, and this shared architecture is why the 2 molecules can interact so directly during transcription. DNA is a double helix, 2 strands wound around each other and held by hydrogen bonds between paired bases. Its sugar is deoxyribose, and it uses 4 bases: adenine, thymine, guanine, and cytosine, with adenine always pairing with thymine and guanine always pairing with cytosine. Because the strands are complementary rather than identical, Either one contains all the information needed to rebuild the other, which is the mechanical basis of replication. RNA differs in exactly 3 ways. It's usually single-stranded, its sugar is ribose rather than deoxyribose, and it substitutes uracil for thymine, so adenine pairs with uracil. Everything else is shared with DNA, and these differences reflect its role as a disposable working molecule rather than permanent storage. 3 types of RNA divide the labor of protein synthesis. Messenger RNA carries the coded message from the nucleus to the ribosomes. Transfer RNA delivers amino acids matched to that message, and ribosomal RNA combines with proteins to form the ribosome itself. Question 37. A skeletal muscle cell contracting rapidly hydrolyzes the terminal phosphate bond of its energy currency molecule to power the interaction of actin and myosin. Which set of products results from breaking that one bond? Your options are A. Adenosine diphosphate, an inorganic phosphate group, and released energy. B. Adenosine monophosphate, 3 inorganic phosphate groups and released energy. C. Adenosine ribose and released energy. D. Glycogen, an inorganic phosphate group, and released energy. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is A. Adenosine diphosphate, an inorganic phosphate group, and released energy. Is correct because breaking the outermost of the 3 high-energy phosphate bonds of adenosine triphosphate removes a single phosphate group. The products are adenosine diphosphate, 1 inorganic phosphate, and a burst of usable energy. B is wrong because adenosine monophosphate results only when a second phosphate is removed, and it would be accompanied by 2 free phosphates rather than 3. Hydrolyzing one bond cannot strip the entire tail. C is wrong because adenosine is the combination of adenine and ribose, so listing them as separate products misstates the structure. The phosphate tail, not the sugar, is where the energy is stored and released. D is wrong because glycogen is a storage polysaccharide and is unrelated to the structure of this molecule. Its breakdown supplies fuel that helps regenerate the energy currency, but is not a product of the reaction. Chemical energy stored in fat or glucose is real, but it's like equity in a house. It can't be handed to a cashier. Cells need a common spendable currency, and that currency is adenosine triphosphate, or ATP. ATP is built from adenine and ribose, forming adenosine, attached to a tail of 3 phosphate groups. Those phosphates all carry negative charge, so cramming them together creates a strained high-energy molecule, and breaking that terminal bond releases a burst of usable energy. Breaking the terminal phosphate bond turns ATP into ADP plus a free phosphate, releasing energy the cell can use. If more energy is needed, a second phosphate comes off to form AMP. Because the process is fully reversible, cells regenerate ATP from fuel energy rather than making new molecules from scratch. ATP's energy funds 3 categories of work. Mechanical work moves things like a contracting muscle. Transport work moves substances against their gradient like the sodium-potassium pump. Chemical work drives the synthesis reactions that build the body's molecules. Without ATP, cells cannot function. Cyanide poisoning and rigor mortis both show what happens when the supply fails. Remember, glucose holds far more total energy but needs processing, while ATP holds less energy per molecule but spends it instantly. Question 38. The immune system distinguishes the body's own cells from foreign invaders by reading a fuzzy, sticky coating of short carbohydrate chains attached to proteins and lipids on the outer surface of the plasma membrane. This coating is unique to each cell type and acts as a cellular identity badge. What is it called? Your options are A. The basement membrane, B. The glycocalyx, C. The cytoskeleton, D, the phospholipid bilayer. Which would you go with? Lock it in before the reveal. The correct answer is B, the glycocalyx. B is correct because the glycocalyx is formed by the sugar chains of glycoproteins and glycolipids on the membrane's external face. Because its pattern is specific to each cell type, it allows the immune system to identify self from non-self. A is wrong because the basement membrane is a layer of extracellular material anchoring epithelial tissue to the connective tissue beneath it. It is a tissue-level structure rather than a coating on a single cell surface. C is wrong because the cytoskeleton is the internal network of microfilaments, intermediate filaments, and microtubules that supports the cell from within. It lies inside the membrane, not on its outer face. D is wrong because the phospholipid bilayer is the lipid framework of the membrane itself. Its heads face the watery fluids, but the carbohydrate identity chains are attached to proteins and lipids rather than being the bilayer. An immune cell must constantly judge which cells belong to the body, and that judgment depends entirely on what's built into the plasma membrane's outer surface. To understand what the immune system reads, we need to understand how the membrane itself is constructed. The accepted description is the fluid mosaic model. Fluid means the components drift freely within the plane of the membrane, and mosaic means it's a mixture of many different molecules rather than a uniform sheet. The framework is a phospholipid bilayer. Hydrophilic heads face the water on both sides, while hydrophobic tails point inward, creating a self-sealing, water-repelling core. Integral proteins, including transmembrane proteins, span this framework as channels, receptors, and enzymes, while peripheral proteins attach loosely to anchor the cytoskeleton, and cholesterol wedges between the tails to keep fluidity balanced in both hot and cold conditions. On the outer surface, sugar chains attach to proteins and lipids to form glycoproteins and glycolipids, together creating the fuzzy glycocalyx coating. Because its composition is specific to each cell type, it acts as a molecular identity badge, which is exactly what immune cells read, and it's why blood typing and transplant compatibility depend on these surface markers. Exam questions describe a fuzzy coating on one cell to signal the glycocalyx, but don't confuse it with the basement membrane, which anchors an entire epithelial sheet to connective tissue. The discriminator is scale. A single cell's coating is the glycocalyx. A whole tissue layer is the basement membrane. Question 39. An instructor asks which statement belongs to the cell theory. The set of principles that anchors the modern understanding of living organisms. Which statement is one of those principles? Your options are: A. Cells can arise spontaneously from non-living organic material when conditions are favorable. B. All cells in the human body are structurally identical and differ only in their location. C. The chemical level is the smallest level of organization at which something can be considered alive. D. All cells arise from pre-existing cells through the process of cell division. Don't overthink it, which one feels right? The correct answer is D. All cells arise from pre-existing cells through the process of cell division. D is correct because one of the core statements of the cell theory is that new cells come only from the division of existing cells, a principle summarized as omnicellular e-cellular. It rules out spontaneous generation entirely. A is wrong because spontaneous generation is precisely what the cell theory rejects. Cells never form from non-living material. B is wrong because the human body contains roughly 200 distinct cell types, varying enormously in size and shape according to their jobs. Uniformity is the opposite of what is observed. C is wrong because the cell theory identifies the cell, not the chemical level, as the smallest unit of life. Atoms and molecules are not alive on their own. For centuries, people believed maggots and mice sprang spontaneously from rotten meat and grain. It took the microscope and rigorous experiments to overturn that idea and establish the cell theory, one of biology's foundational frameworks. The theory makes several claims. The cell is the basic structural and functional unit of life. All organisms are made of one or more cells. All cells arise only from pre-existing cells dividing, and the continuity of life rests on the cellular basis. Molecules can be astonishingly complex without being alive. Hemoglobin, DNA, and even a whole ribosome are sophisticated. But life only begins where a boundary encloses a self-maintaining, self-reproducing chemical system, and that level is the cell. Despite roughly 200 distinct cell types across 30 to 40 trillion cells, every human cell shares a common architecture: the plasma membrane, the cytoplasm with its organelles, and the nucleus as control center, each shaped to fit its job. A good theory earns its status by what it forbids. Cell theory rules out spontaneous generation, rules out life existing below the cellular level, and rules out any healing or growth that doesn't come from dividing cells, which is exactly why cancer and scarring make sense within it. Question 40. A cardiac muscle cell must contract continuously for a lifetime, and therefore has an enormous, unrelenting demand for usable energy. Under the microscope, its cytoplasm is packed with double membrane organelles whose inner membrane is thrown into deep folds. Which organelle is present in such abundance and why? Your options are: A. Lysosomes, because cardiac tissue recycles worn organelles at an unusually high rate. B. Peroxisomes, because cardiac tissue must neutralize large volumes of free radicals. C. Mitochondria, because cardiac tissue generates most of its energy through aerobic respiration. D. Smooth endoplasmic reticulum, because cardiac tissue synthesizes large quantities of lipid. Got a guess? Lock it in. The correct answer is C. Mitochondria, because cardiac tissue generates most of its energy through aerobic respiration. C is correct because mitochondria are enclosed by a double membrane whose inner layer folds into cristae, and they are the site where most cellular energy is produced through aerobic respiration. Tissues with high energy demand, including cardiac muscle, liver, and kidney, carry the largest numbers of them. A is wrong because lysosomes are single membrane sacs of digestive enzymes that break down worn organelles and engulfed debris. They lack cristae and are not the site of energy production. B is wrong because peroxisomes are single membrane sacs containing oxidase and catalase that detoxify harmful substances and neutralize free radicals. They are most numerous in liver and kidney cells rather than cardiac muscle. D is wrong because smooth endoplasmic reticulum is a network of tubules without ribosomes that handles lipid synthesis, detoxification, and calcium storage. Its structure is a branching network rather than a double-membraned organelle with folded cristae. A heart cell contracts once every second, non-stop for an entire lifetime, and that relentless work demands enormous energy. Under a microscope, this need shows up as a cytoplasm packed with mitochondria, organelles whose abundance directly reflects how hard a cell works. Every mitochondrion has two membranes, a smooth outer membrane forming the boundary, and an inner membrane folded into cristae. Those folds matter because the energy-producing reactions happen right on that inner membrane, so folding multiplies the working surface without making the organelle any bigger. Mitochondria carry strange features that give away their history: their own small loop of DNA, their own ribosomes, and the ability to divide on their own rather than being built by the cell. These are leftovers from an ancient bacterium that was engulfed and became a permanent resident, which is why mitochondrial DNA is passed down separately from nuclear DNA. Exam questions hinge on telling mitochondria apart from lookalikes. Lysosomes hold digestive enzymes. Peroxisomes handle detoxification and free radicals. Smooth ER manages lipids and calcium. And rough ER is studied with ribosomes for protein processing. Only mitochondria show a double membrane with cristae. Whenever a stem describes a double membrane with folds, or a highly active tissue like heart or liver or kidney, it's pointing straight at mitochondria. Question 41. A physiology instructor lists 4 membrane transport processes on the board and asks, which one obligates the cell to spend adenosine triphosphate? The class must distinguish processes driven by the cell's own energy from those driven by gradients and pressure. Which process requires the cell to expend energy? Your options are A. Glomerular filtration in the kidney driven by blood pressure. B. The sodium and potassium pump moving both ions against their gradients. C. Osmosis of water across a membrane toward the more concentrated solution. D. Facilitated diffusion of glucose through a carrier protein. Which one is it? Pause the video if you need more time. The correct answer is B. The sodium and potassium pump moving both ions against their gradients. B is correct because active transport moves a substance against its concentration gradient, which cannot happen spontaneously and therefore consumes energy. The sodium and potassium pump uses one molecule of adenosine triphosphate to drive 3 sodium ions out and 2 potassium ions in. A is wrong because filtration is passive and is powered by a hydrostatic pressure gradient rather than by cellular energy. Blood pressure supplies the push in the kidney, not the tubule cells. C is wrong because osmosis is the passive diffusion of water down its own concentration gradient, using nothing but the kinetic energy of the water molecules. Aquaporins speed it up without spending energy. D is wrong because facilitated diffusion uses a transport protein but still moves the substance down its gradient. The protein provides a passage, not a power source. The sodium-potassium pump alone consumes a huge share of the body's energy, running non-stop in every cell. That single fact reveals the real principle behind membrane transport. Some movements are free and some must be paid for. Passive processes need no cellular energy because the substance is simply moving downhill the way it would anyway. Active processes require the cell to spend energy to push something uphill against its gradient. Whether a protein helps out is irrelevant. Only the direction of movement decides which category applies. 4 processes are passive. Simple diffusion moves small non-polar molecules straight through the lipid bilayer, while facilitated diffusion uses a protein to move larger or polar molecules down their gradient. Osmosis moves water toward the more concentrated solution, and filtration pushes water in solutes by hydrostatic pressure, from higher to lower pressure. 3 processes are active. Primary active transport draws energy directly from ATP hydrolysis at the transporter, while secondary active transport spends energy already stored in a gradient built earlier. Vesicular transport moves bulk material in membrane-bound sacs through endocytosis and exocytosis, requiring energy for the membrane rearrangement. Each cycle of the sodium-potassium pump spends 1 ATP to push 3 sodium ions out and pull 2 potassium ions in, both against their gradients. Because every cell runs this pump continuously, the steep gradients it creates power nerve impulses, muscle contraction, and the resting membrane potential of about negative 70 millivolts. Question 40. Oxygen slips directly through the lipid core of the plasma membrane, while glucose, a molecule of similar physical size, cannot and must be carried across by a protein. As glucose delivery increases, the rate of glucose entry eventually plateaus even though more glucose is available outside. Which explanation accounts for both observations? Your options are A. Oxygen is small and nonpolar, so it crosses the bilayer directly, while glucose is polar and needs carrier proteins that can become saturated. B. Oxygen is transported by channel proteins that never saturate, while glucose crosses the bilayer directly and is limited by its concentration. C. Oxygen crosses by active transport powered by adenosine triphosphate, while glucose crosses passively and reaches equilibrium. D. Oxygen is drawn across by hydrostatic pressure, while glucose is drawn across by osmotic pressure and stops when pressures equalize. Take a second, which answer would you pick? The correct answer is A. Oxygen is small and non-polar, so it crosses the bilayer directly, while glucose is polar and needs carrier proteins that can become saturated. A is correct because the hydrophobic interior of the bilayer admits small, non-polar lipid-soluble molecules such as oxygen and carbon dioxide by simple diffusion. Polar molecules like glucose require carrier proteins, and because those carriers exist in limited numbers, transport saturates once all of them are occupied. B is wrong because this reverses the two mechanisms. Oxygen needs no protein at all, and glucose cannot penetrate the hydrophobic core on its own. C is wrong because neither substance is moving against its gradient in this scenario, so no energy is required for either. Oxygen diffusion is the classic example of a passive process. D is wrong because hydrostatic pressure drives filtration across capillary walls, not gas movement into cells. Osmotic pressure governs water movement rather than glucose entry. Oxygen and glucose are similar in size, yet one glides through the plasma membrane freely while the other cannot cross at all without help. The answer is in size. It's what the membrane's interior is made of. The plasma membrane is selectively permeable because its core is made of fatty acid tails, a hydrophobic layer that anything crossing must pass through. Small, non-polar, lipid-soluble molecules like oxygen and carbon dioxide tolerate that environment and diffuse straight across with no protein needed. Charged ions and polar molecules like glucose can't tolerate the fatty core, so they rely on transport proteins instead. Channel proteins form water-filled pores, often gated, while carrier proteins bind the molecule, change shape, and shuttle it across. Facilitated diffusion has a limited number of proteins, so it saturates, it spikes. The rate plateaus once every protein is occupied, while simple diffusion keeps rising with the gradient. And a common trap, using a protein doesn't mean energy is spent, since the substance still moves down its own gradient. ATP only enters the picture when movement goes against that gradient. Question 43. A laboratory error results in red blood cells being placed in a container of distilled water rather than normal saline. Within moments, the cells swell and rupture. Which term describes the solution and what accounts for the outcome? Your options are A. Isotonic, because solute concentrations inside and outside the cell were equal, so no water moved. B. Hypertonic, because the outside solution held more solute, so water left the cells. C. Hypertonic, because the outside solution held less solute, so water moved into the cells until they burst. D. Hypertonic, because the outside solution held more solute, so water moved out and the cells crenated. Before I reveal it, which one do you think is right? The correct answer is C. Hypertonic, because the outside solution held less solute, so water moved into the cells until they burst. C is correct because a hypertonic solution contains a lower solute concentration than the cell interior, and distilled water is the extreme case. Water moves by osmosis toward the higher solute concentration inside the cell, swelling it until the membrane fails, an event called hemolysis in red blood cells. A is wrong because an isotonic solution such as normal saline produces no net water movement and leaves cells at normal volume. That is exactly the outcome that did not occur here. B is wrong because a hypertonic solution pulls water out of cells and makes them shrink and shrivel. The cells in this scenario gained water and burst. D is wrong because the tonicity term is correct, but the explanation contradicts it. Hypertonic means less solute outside, and crenation is the hypertonic outcome. Why does the wrong IV fluid destroy cells instead of helping them? The answer lies in one process, osmosis, the movement of water across a membrane, and its clinical cousin, tonicity. Osmosis is water diffusing toward the side with more dissolved solute. It can cross the membrane slowly on its own, or rush through special channels called aquaporins, which is why cells that need fast water movement are packed with them. Tonicity describes the solution, not the cell. In an isotonic solution, nothing changes. In a hypertonic solution, water rushes in and the cell swells, even bursting in a process called lysis. In a hypertonic solution, water leaves and the cell shrinks, called crenation. Picture the same red blood cell dropped into 3 solutions. In hypertonic fluid, water floods in and it bursts. In isotonic fluid, it holds its normal shape. In hypertonic fluid, water drains out and it shrivels into crenation. Clinically, this is why plain water EV causes hemolysis, and why hyponatremia swells brain cells with nowhere to expand. On exams, forget memorizing prefixes. Just ask where the solute is concentrated, and the water movement follows. Question 44. Glucose is absorbed from the small intestine into the lining cells, even when glucose is already more concentrated inside those cells than in the intestinal contents. The energy for this uphill movement comes from sodium flowing back into the cell down a gradient that a pump established earlier. Which process is this? Your options are A. Simple diffusion, because glucose ultimately follows its own gradient. B. Facilitated diffusion, because a carrier protein is involved. C. Primary active transport, because adenosine triphosphate is hydrolyzed at the moment glucose crosses. D. Secondary active transport, because the energy comes from a previously established sodium gradient. What's your answer? Commit to one before I continue. The correct answer is D. Secondary active transport, because the energy comes from a previously established sodium gradient. D is correct because secondary active transport moves a substance against its gradient using energy stored in the gradient of another substance, usually sodium. The pump spends the energy earlier to build the sodium gradient, and glucose rides along as sodium flows back in, which is why the process is called secondary. A is wrong because simple diffusion moves substances down their gradient through the bilayer with no protein and no energy. Glucose here is moving uphill against its own gradient. B is wrong because facilitated diffusion also requires movement down the gradient, with the protein serving only as a passage. Uphill movement rules it out. C is wrong because in primary active transport, energy is drawn directly from hydrolysis of adenosine triphosphate at the transporter itself. Here, the energy was spent earlier by a separate pump. Glucose can move into intestinal cells even against its own concentration gradient, uphill, without any ATP being consumed at the transporter itself. This puzzle is solved by understanding secondary active transport. Primary active transport spends ATP directly at the pump, as in the sodium-potassium pump, where 3 sodium ions move out and 2 potassium ions move in. Secondary active transport separates the energy spending from the transport event. The sodium pump builds a steep gradient first, and that gradient is spent later. That sodium gradient is a stored form of potential energy, much like water held behind a dam. When sodium flows back downhill into the cell, a transport protein harnesses that flow to drag glucose along with it, even against glucose's own gradient. When 2 substances move in the same direction, it's called symport or co-transport, as with sodium-linked glucose absorption. When they move in opposite directions, it's called antiport or countertransport. This is the basis of oral rehydration therapy. A solution with both sodium and glucose engages the co-transporter, pulling water in osmotically along with them, which is why plain water alone cannot rehydrate someone as effectively during severe diarrhea. Question 45. A macrophage patrolling infected tissue encounters a bacterium, extends arm-like projections around it, and engulfs the entire organism inside a membrane-bound sac drawn in from the cell surface. Which process has occurred? Your options are A. Exocytosis, because a vesicle fuses with the plasma membrane. B. Phagocytosis, a form of endocytosis in which large solid particles are engulfed. C. Pinocytosis, in which droplets of extracellular fluid are taken in nonspecifically. D. Receptor-mediated endocytosis, in which specific molecules bind membrane receptors before uptake. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is B. Phagocytosis, a form of endocytosis in which large solid particles are engulfed. B is correct because phagocytosis is the form of endocytosis in which large solid particles such as bacteria, debris, or dead cells are engulfed. Protective cells including macrophages and certain white blood cells extend pseudopods around the target, which is exactly what is described. A is wrong because exocytosis moves material out of the cell when a vesicle fuses with the plasma membrane and releases its contents. The direction described is inward. C is wrong because pinocytosis brings in droplets of extracellular fluid and whatever solids happen to be dissolved in them. It is non-selective and handles fluid, not whole bacteria. D is wrong because receptor-mediated endocytosis begins with specific molecules binding to membrane receptors, and it handles targets such as low-density lipoprotein, iron, and certain hormones. Engulfing a whole organism with pseudopods is a different mechanism. A bacterium is far too big for any channel or carrier protein to move across the membrane. When the cargo is bulk material rather than a dissolved solute, the cell needs bulk transport instead. Vesicular transport moves large particles, macromolecules, and bulk fluid inside membrane-bound sacs called vesicles. It costs ATP because deforming and resealing a membrane is real mechanical work, and it runs in one of two directions: endocytosis bringing material in, or exocytosis sending material out. In phagocytosis, a macrophage extends pseudopods around a bacterium, wraps it entirely, and pinches off the membrane to enclose it in a phagosome, a vesicle formed from the cell's own membrane. Phagocytosis engulfs solid particles like bacteria and debris. Pinocytosis takes in fluid droplets non-selectively. Receptor-mediated endocytosis selectively grabs molecules like LDL, cholesterol, iron, or hormones after they bind a receptor. Exocytosis runs the opposite direction, releasing hormones, enzymes, neurotransmitters, and mucus out of the cell. On exam stems, identify the direction of movement first. Then ask what's being engulfed and whether it's selective. That combination of two features points straight to the right mechanism. Question 46. A cell biologist tracks a cell through interphase and notes the stage at which each chromosome becomes two identical sister chromatids joined together, guaranteeing that both future daughter cells will inherit a complete genetic blueprint. Which stage of interphase is this? Your options are A. S phase, B. G1 phase, C. G2 phase, D. GA phase. Which would you go with? Lock it in before the reveal. The correct answer is A. S phase. A is correct because the S phase or synthesis phase is when the cell replicates its DNA. After it finishes, each chromosome consists of 2 identical sister chromatids joined at the centromere. B is wrong because the first gap phase is a period of growth, protein and organelle synthesis, and routine metabolic work. It is typically the longest and most variable stage but involves no DNA copying. C is wrong because the second gap phase completes growth, produces the proteins and microtubules needed for division, and checks the replicated DNA for errors. It follows replication rather than performing it. D is wrong because cells that will never divide again, such as most neurons, exit the cycle into a resting state and remain there. No DNA replication occurs in that state at all. Interphase was once called the resting stage of the cell cycle, but that name was so misleading it's been abandoned. A cell in interphase is doing every job it exists to do, while also building a complete second copy of its genome. Interphase subdivides into 3 stages plus 1 exit ramp. The first gap phase, G1, handles growth and routine metabolism. The synthesis phase, S, replicates the DNA. The second gap phase, G2, finishes growth and checks the new DNA for errors. Cells like neurons and cardiac muscle can exit permanently into G0, which is why heart and nerve damage rarely heals. Here's why replication is called semi-conservative. Helicase unwinds the double helix by breaking the hydrogen bonds between paired bases. Each strand then acts as a template, and DNA polymerase builds a new complementary strand by matching adenine with thymine and guanine with cytosine. So each new molecule ends up with 1 old strand and 1 new one. After replication, each chromosome consists of 2 identical sister chromatids joined at the centromere. This is a change in structure, not in chromosome number. The cell doesn't have twice as many chromosomes after synthesis. It has the same number, each one now doubled. So whenever an exam stem mentions a chromosome made of 2 identical chromatids, it's describing the outcome of the synthesis phase specifically. Question 47. Viewing a dividing cell under the microscope. A student sees the chromosomes lined up single file along an imaginary plane across the middle of the cell, with spindle fibers attached to their centromeres from both poles. Which stage of mitosis is being observed? Your options are prophase, B. telophase, C. metaphase, D. anaphase. Don't overthink it. Which one feels right? The correct answer is C. metaphase. C is correct because metaphase is defined by chromosomes aligning single file along the metaphase plate at the cell's equator. This alignment guarantees that each daughter cell receives exactly 1 copy of every chromosome once the chromatids separate. A is wrong because prophase is when chromatin condenses into visible chromosomes. The nuclear envelope and nucleolus break down, and the spindle begins to form. The chromosomes are not yet aligned at that point. B is wrong because telophase reverses prophase, with chromosomes uncoiling, new nuclear envelopes forming, nucleoli reappearing, and the spindle breaking down. The chromosomes have already reached the poles by then. D is wrong because anaphase begins when centromeres split and sister chromatids are pulled apart toward opposite poles. Movement away from the equator marks it, not alignment at the equator. A dividing cell moves through a fixed sequence of stages, so a single snapshot under a microscope can reveal exactly where in that sequence the cell sits. Let's break down what distinguishes each stage. Before the stages, separate 2 commonly confused terms. Mitosis is division of the nucleus, distributing duplicated chromosomes into 2 daughter nuclei, while cytokinesis is division of the cytoplasm, physically splitting 1 cell into 2. In prophase, chromatin condenses into visible chromosomes as the nuclear envelope dissolves and the spindle forms. In metaphase, chromosomes align at the metaphase plate, guaranteeing equal division. In anaphase, centromeres split and chromatids, now full chromosomes, are pulled to opposite poles. In telophase, nuclear envelopes reform and cytokinesis pinches the cell into two. Division is tightly regulated. Growth factors stimulate division. Contact inhibition halts it once cells touch their neighbors. Internal checkpoints verify conditions are safe, and tumor suppressor genes act as molecular brakes while proto-oncogenes act as accelerators. Cancer occurs when brakes fail, accelerators stick, and cells ignore checkpoints and contact inhibition, dividing relentlessly. Because treatments target fast-dividing cells, they also strike normal fast-dividing tissue, explaining chemotherapy's hair loss and gut side effects. Question 88. Before a protein can be built, the instructions stored in a gene must be copied into a portable form that can leave the control center and reach the site of assembly. This copying step occurs inside the nucleus and uses a specific enzyme. Which statement describes the stage accurately? Your options are: A. It is translation. It occurs at the ribosome and it produces messenger RNA. B. It is translation. It occurs in the nucleus and it produces a polypeptide chain. C. It is transcription. It occurs at the ribosome and it produces transfer RNA. D. It is transcription. It occurs in the nucleus and RNA polymerase produces messenger RNA. Got a guess? Lock it in. The correct answer is D. It is transcription. It occurs in the nucleus and RNA polymerase produces messenger RNA. D is correct because transcription is the copying of a gene from DNA into messenger RNA, carried out by RNA polymerase inside the nucleus. The resulting messenger RNA leaves through a nuclear pore because DNA itself is too large and too valuable to exit. A is wrong because translation happens at the ribosome and produces a polypeptide, not messenger RNA. Messenger RNA is an input to translation rather than its product. B is wrong because translation does produce a polypeptide chain, but it occurs in the cytoplasm at the ribosome rather than in the nucleus. Placing it in the nucleus mixes the two stages. C is wrong because the stage is named correctly but placed in the wrong location with the wrong product. Transfer RNA delivers amino acids during translation and is not the copy of a protein coding gene. DNA never leaves the nucleus, but proteins are built at ribosomes out in the cytoplasm. To solve that distance problem, the cell makes a disposable copy of one gene and sends it out instead, a process called transcription. The overall pathway runs from DNA to RNA to protein, known as the central dogma. A gene is a stretch of DNA written in a 4-letter base alphabet, read 3 letters at a time as codons, with 64 possible codons covering 20 amino acids plus start and stop signals. Enough redundancy that most amino acids get more than one codon. RNA polymerase binds the promoter, unwinds the DNA, and uses one strand as a template to assemble a complementary messenger RNA strand. When it reaches the end of the gene, the mRNA detaches, the DNA rewinds, and the transcript exits through a nuclear pore. The one key substitution, RNA uses uracil instead of thymine, so a template adenine specifies uracil. Everything else pairs normally. Thymine specifies adenine, guanine specifies cytosine, and cytosine specifies guanine. Transcription writes a copy in the same language, nucleic acid to nucleic acid, while translation converts that message into a different language, amino acids. Remember it by location and product. Transcription happens in the nucleus and yields RNA. Translation happens at the ribosome and yields a polypeptide. Question 49. At the ribosome, a messenger RNA codon reading GCA is positioned in the active site, and a transfer RNA molecule arrives carrying the amino acid alanine. For this delivery to be correct, the transfer RNA must display a matching 3-base sequence at its opposite end. What must that sequence be, and what is it called? Your options are A. CGU, and it is called an anticodon. B. GCA, and it is called an anticodon. C. CGT, and it is called a codon. D. TAC, and it is called a triplet. Which one is it? Pause the video if you need more time. The correct answer is A. CGU, and it is called an anticodon. A is correct because A transfer RNA carries an anticodon that is complementary to the messenger RNA codon it must recognize. Pairing G with C, C with G, and A with U converts the codon GCA into the anticodon CGU. B is wrong because an identical sequence would not pair with anything, since base pairing requires complementary bases rather than matching ones. Two identical strands would repel rather than bind. C is wrong because the sequence uses thymine, which does not appear in RNA at all. It also misnames the sequence since the codon sits on the messenger RNA rather than on the transfer RNA. D is wrong because this sequence uses thymine and does not complement the given codon. A triplet is the 3-base unit as it appears on DNA, not the recognition sequence on a transfer RNA. Nucleotide sequences and amino acid sequences use completely different chemical languages, so translating between them requires a dedicated interpreter molecule. That molecule is transfer RNA. Translation happens at ribosomes and requires all 3 types of RNA working together. Messenger RNA supplies the codons. Ribosomal RNA forms the ribosome that holds everything in place and forges peptide bonds, and transfer RNA delivers each amino acid. The entire codon on a transfer RNA is complementary to a specific codon on messenger RNA. Adenine pairs with uracil and guanine pairs with cytosine. So a codon reading guanine cytosine adenine is recognized by an anticodon reading cytosine guanine uracil, guaranteeing the correct amino acid arrives every time. The order of codons in messenger RNA fixes the order of amino acids, which is the protein's primary structure, and everything downstream, including folding and function, follows from that sequence. A single substituted amino acid in hemoglobin is enough to cause sickle cell anemia. Remember the 3 terms: a triplet sits on DNA, a codon on messenger RNA, and an anticodon on transfer RNA. And if a sequence contains thymine, it cannot be RNA, so rule that out before you even start pairing bases. Question 50. A histology slide shows a tissue in which relatively few cells are widely scattered within a large volume of non-living material made of ground substance and protein fibers. The instructor notes that this arrangement is what gives bone, cartilage, tendon, adipose tissue, and blood their very different properties despite their shared classification. Which primary tissue type is shown? Your options are epithelial tissue, B. connective tissue, C. muscle tissue, D. nervous tissue. Take a second. Which answer would you pick? The correct answer is B. Connective tissue. B is correct because connective tissue is defined by having relatively few cells separated by an abundant extracellular matrix of ground substance and protein fibers. Because the composition of that matrix varies so widely, one tissue class can include structures as different as bone, cartilage, fat, tendon, and blood. A is wrong because epithelial tissue has cells packed tightly together with almost no extracellular material, always presents a free apical surface, and is avascular. Abundant matrix is the opposite of its defining feature. C is wrong because muscle tissue consists of cells densely packed with the contractile proteins actin and myosin, and is specialized to shorten forcefully. Its defining property is contraction, not matrix. D is wrong because nervous tissue consists of neurons that generate and conduct electrical signals plus supporting neuroglia. It is specialized for rapid communication and has no substantial extracellular matrix. Cells are the smallest living units and organs are the body's working structures, but tissue is the bridge between them. Every one of the body's hundreds of cell types sorts into just 4 primary tissue categories, and every organ is built from some combination of the 4. Epithelial tissue covers surfaces and lines cavities, packed tightly with almost no matrix between cells. Connective tissue is the opposite. Few cells scattered in abundant extracellular matrix, covering everything from bone to blood. Muscle tissue contracts to create movement, and nervous tissue senses stimuli and transmits electrical signals. Epithelial tissue always has one free apical surface exposed to the outside, or a cavity, and one basal surface anchored to connective tissue by a basement membrane. It's avascular, with no blood vessels of its own, and it's classified by layering as simple or stratified, and by cell shape as squamous, cuboidal, or columnar. Muscle tissue contracts using actin and myosin. Skeletal muscle is voluntary and striated. Cardiac muscle is involuntary and striated and found only in the heart. And smooth muscle is involuntary, not striated, and lines organs like the stomach and blood vessels. Nervous tissue contains neurons that generate signals and neuroglia that support them. Whether it's the hardened matrix of bone, the flexible matrix of cartilage, or the liquid plasma of blood, connective tissue is defined by scattered cells sitting in matrix they secreted, not by how that matrix feels. Remember, almost no matrix means epithelium. Abundant matrix means connective tissue. That's a wrap on our complete question and answer guide to Domain 1, Chemistry, Cells and Body Organization. If you'd like extra practice on everything we've covered today, be sure to visit our website. You'll find hundreds of free practice questions, plus complete, easy-to-follow study guides ready whenever you need them. It's a great way to reinforce what you've learned and build your confidence. Check the link in the description to get started. Don't forget to subscribe for our next video, and good luck on your Anatomy and Physiology 1 exam.